to introduce our next speaker, the keynote speaker, Professor Lou Kaufman. Professor Kaufman is Professor Emeritus at University of Illinois at Chicago. His research is in topology, not theory, topological quantum field theory, quantum computing, and fundamental ideas in mathematics and science, including algebra, logic, cybernetics. He's very well known worldwide for the discovery of state summation models in knot theory, the bracket state sum model for the Jones polynomial, or for the not polynomial called the Kaufman polynomial. Whenever I mentioned any contact and collaboration with Professor Louis Kaufman to my colleagues at Los Alamos or worldwide, there was always the same question: is it the Kaufman? They said, yes, this is the one. So he's really famous. He's originator and of a generalization of classic knot theory called virtual knot. Kaufman is a fellow of the American Mathematical Society, very distinguished title. He is an author of numerous books related to knot theory. He is the editor-in-chief and founding editor of the Journal of Knot Theory and its Ramifications, published by World Scientific. He is the editor of the book series on knots and everything, published by World Scientific. And we hope that proceedings of our conference will also be published in this book series. He is the editor of the book series. Okay, Kaufman is a former Polya lecturer for the Mathematical Associations of America, past president of the American Society for Cybernetics, and recipient of Warren McLaughlin and Norbert Wiener Awards of American Society for Cybernetics, and the recipient of Ludwig Berthold Award in Complexity Thinking. He is also recipient of the Lester Ford Award and Lester Ford and Paul Holmes Awards, both from Mathematical Association of America, for expository writing for articles in the American Mathematical Monthly. Thank you, thank you, Professor Kaufman, for giving us this lecture. Please, you have the floor.
Thank you, Hannah. Let's see if I can find my slides. That looks right. Oops, sorry. Okay, right. So the title of this talk is Noncommutative Calculus, Noncommutative Worlds and Relativity. And this is really mostly a talk about calculus and how you can find that it's fruitful to think about it in various ways that are related to non-commutativity. I kind of designed this talk thinking that if I were giving it and Zbigniew were present, he would argue with me a lot. So I wish he were here to argue with me. Let's begin with this slide, which I've entitled From Infinitesimal Calculus to Grossman Algebra. Zero is an excellent number and its square is equal to 0. And there is a concept of infinitesimal whose square is equal to 0. And in the world of Bill LeVere and J. Bell, 0 and that star, that infinitesimal, are indistinguishable. So that you should think of 0 as kind of like an infinitesimal, but on the other hand, they're not the same. And in order to speak that way, they need to use intuitionistic logic. But you can also just say, well, I have a little infinitesimal formal entity and its square is 0, and I'll do calculus with it by the definition that f of x plus star is f of x plus the derivative of f times star. And if you play with this, you'll see that just about everything works. You can do all the calculus you want by just extending the real numbers by this one nearly indistinguishable from 0 element. And even Grossman algebra, which is the point I wanted to make about this. You see, let's go to 3 dimensions. And then we will have nilpotent infinitesimals, dx, dy, and dz. Each one has square 0. But all the infinitesimals should have square 0. So a dx plus b dy plus c dz, that also ought to have square 0. Now, you should ignore the middle of this slide, which is just reminding us that we really can do calculus with this system, and go over here. And then we have that 0 should be dx plus dy squared to do the algebra and multiply it out. And you have that 0 is therefore dx squared plus dy squared plus dx dy plus dy dx. And so dx dy is equal to minus dy dx. And we just arrived at Grossman algebra from the notion of square 0 infinitesimals. So I think this is a very interesting way to get to Grossman algebra. And it shows that calculus really was very non-commutative from the very beginning, except maybe you ignored it. And as I said, the talk is about calculus and varieties of calculus. So I want to look at another variety of calculus. And this is discrete calculus. So my d here is just a difference. The delta n is equal to 1. It could be some other delta, some other d, a change of f divided by some delta, but I'll take delta equal to 1. And I have f of n plus 1 minus f of n as the derivative. And I'll call f hat of n f of n plus 1. So the derivative is really f hat minus f. And then you find that the Leibniz rule is not true, but that doesn't stop you from doing discrete calculus, which is a wonderful subject. You just have to watch the shifts when you're doing the Leibniz rule. And you have that d of f times g is df times g plus f hat times dg. Or another way of putting it is you have df times g plus f times dg plus another product, which I'll leave to you to figure out. But I like this one, a little shift. Because now you see that there's some implicit non-commutativity that can be explicated. Let's take an element j, which doesn't commute with f, but is defined by fj is j f hat. If you pass j from right to left across f, it shifts f up by 1, so you get f of n plus 1. So f of n times j is j times f of n plus 1, and that defines j as a non-commuting element. And then let's define nobl of f to be equal to j df, and you'll see what I did in a moment. So I've changed my derivative by multiplying by this non-commutative element. And then I have nobl of f is j times f hat minus f minus f being the difference. That's jf hat minus jf. But jf hat is fj. So you see, nobl is the commutator of f with j. And so the discrete derivative becomes a commutator. And the moral of this story is that if you were to define derivatives as derivations, as actions by a commutator, and they do satisfy the Leibniz rule, mind you, why then you can embed discrete calculus into a non-commutative calculus, then it would be closer to ordinary calculus in that it would satisfy the Leibniz rule. So discrete calculus is also very close to non-commutativity in a somewhat different way than the Grossman algebra. And this is the one that I'm going to be talking about mostly today, is thinking of derivatives as commutators. Oh, I have here the exercise. You could look at it for a moment. That it's going to check for us that nobl of fg indeed satisfies the Leibniz rule, because you see it quite clearly as an adjustment here. I multiplied by j, and I have jf hat, but jf hat is fj. And now we have j df and j dg, and that's nobla f and nobla g. And so there's the Leibniz rule. And you can take this as a proof that derivations defined by commutators satisfy the Leibniz rule, if you like. Now, an old motivation for what I've been thinking about is a paper by Dyson about a derivation by Feynman, in which Feynman showed Dyson how to get the Maxwell's equations from what looks like the rules for quantum mechanics, that you have positions that commute, you have positions that don't commute with momenta, but delta ij them. And then Feynman plays with this setup and shows that you can define an E and an H, and they will satisfy Maxwell's equations. One way of putting it is the way I put it here, stripping things of the physical terms. So I have xi and xj dot are delta ijing one another, and the xi's commute. The xj dots are not commuting, of course. That's part of the assumption. And since they're not commuting, I'm going to let the H field, the magnetic field, will correspond to the cross product of x dot with itself. And that isn't zero because of the fact that the elements don't commute with one another. And then you find that you can define E and H by way of the Lorentz force law. And it all works. I think we won't have time to show you the derivation of this, but I actually am concerned with simple ways of arriving at Maxwell's equations that are historically interesting. So this is one of them. And in this one, you see the idea of letting the derivatives be defined by commutators is implicit in the setup, because you see that you could think, looking at this commutator, oh, well, the derivative of xi with respect to xj is delta ij. So that says that taking the derivative with respect to xi is the same as taking the commutator with the dot. So the derivative of anybody with respect to xj is the commutator with xj dot in this setup. And so all the derivatives in this Feynman-Dyson derivation are actually being represented by commutators, except for the time derivatives, and that's an interesting story. Of course, you might represent them by a commutator as well. A long time ago, Pierre Noyes and I wanted to try to think about this from the point of view of discrete physics. And it was that question of how would this look in discrete physics that led us to think about formulating discrete calculus in terms of commutators. But now let me go farther back in history. Hermann Weyl wrote a book entitled Space-Time Matter. And in that book, he had the insight that electromagnetism came from the properties of a line element in space-time. And if I say it that way, there's absolute truth in it. He tried to make a theory out of it, and that theory went through various modifications before it turned into its final form, and we'll mention that. But the absolute truth of the matter is a little bit of exercise in differential forms that Hermann Weyl did, and let's look at it just for the fun of it. My notion here is that I don't want to rush. These historical things and so on are very interesting. So here's a one form in space-time. And of course, I've taken some care to get my signs right. You wouldn't necessarily know to take the right signs to begin with, but it's a one form, space-time one form. And I'm going to look at the differential of the one form. And you'll recall that when you take the differential of the form, you take the total differentials of the functions involved, and then you use the Grossman algebra to recollect the terms. And that means that a dx times a dx is 0, and a dx times a dy is a minus dy times dx. And so you take the d, and you find, oh, what do you find? Well, if you collected up the space terms and called them A, then you're looking here at the curl of A. And then here's this phi, which we might as well, with malice aforethought, call the scalar potential. And then we see that we have space derivatives of the scalar potential and time derivatives of the elements in the vector potential, which is this part, FGH. And so we can summarize what we found by saying that if we were to set the d lambda to be terms b1, b2, b3, and e1, e2, e3, then and call FGH A and phi the scalar potential, why then the E, the terms involving time, is minus the scalar potential minus the derivative of the vector potential with respect to time. And the B is the curl of A. And one recognizes that as the way that the electromagnetic field comes from a potential. So Hermann Weyl is observing that if you think of a differential form, then when you take the d of that differential form, you land exactly on the form of the electromagnetic field. And then you can ask, well, what does that mean? In particular, it means that the E and the B will satisfy some relations because d squared lambda 0 is a fact of life. And if you compute d squared lambda equals 0 in the same way I was just doing, you find that it says that del dot B is 0 and that del cross E plus nabla cross E plus dB dt is equal to 0, which are the Maxwell equations for E and B. And the other two Maxwell equations involve charge and current and can be regarded as defined in this way, if you like. And then we have electromagnetic theory coming from a line element. And that would mean that if you had a non-zero electromagnetic field, then integration along that line element would differ depending on what path you took. And so Weyl had the idea that he could add to the geometry of general relativity the notion that there would be a special line element whose holonomy was very important for producing the electromagnetic field. The electromagnetic field at a point would be the result of doing a little holonomial on that line element around the point. And the way the electromagnetic field acts as you go from one point to another would be related to the difference between integrating along one path or integrating along another. And he made the attempt to unify this with general relativity, with this line element being geometrical. Einstein criticized it on the basis that, well, this would say, remember, it's a temporal spatial line element. Clocks wouldn't be transported precisely. There would be problems with thinking about the evidence that we have of the exactness of spectral lines, other things. So it was criticized as a purely geometrical theory. But then Fritz London, a little later on, discovered that he could put it into the phase of the wave function. When Weyl did this, quantum theory hadn't quite gotten formulated. Sometime later, it became reinterpreted as the phase of the wave function. And interpreted that way, it made perfect sense, and it led to, eventually, genuine physical effects, such as the Aharonov-Bohm effect, which shows that a potential alone with no fields present can influence the phase of a wave function in quantum mechanics. So what Weyl had walked into was something that was in between the geometry and the quantum theory, and it remains, of course, not fully understood to this day because there is no full unification of relativity and quantum theory. So I remind you what some of this looks like. You would integrate the potential along a path, and when you do that, you can have an interference experiment, where those phases will, though the interference resulting from those phase changes can be observed. So Weil's idea and its effects can be observed at the quantum level. Now there's formalism involved here and generalizations as well. The line element got generalized to what are called gauge connections, where instead of having simply scalar coefficients, the coefficients are matrices, linear transformations that are acting on some internal space. And then this becomes gauge theory. And one can generalize the notion of taking D of the form to D of it plus A wedge A, where A is that. And of course, now things have become non-commutative because these are matrices, and these become the Yang-Mills fields, and were pioneered by Yang, and of course, and this formula for the curvature with this extra term here comes from covariant derivatives, which are di's plus the potentials I, because when you take the commutator, you get curvature by taking the commutator of covariant derivatives. So you take delta I delta j minus delta j delta I, and then you get this nice formula for the commutator of delta I and delta j. And that is the field. That's D of the differential form with its extra part. And that's the field for the Yang-Mills field, and also for the electromagnetic field, if these are simplified again. And this is a very familiar formula for the electromagnetic field. So this is the way it happened. And here I'm being too pedantic and just writing it out, and I needn't do that. But this part is worth mentioning, although we're not going here today. And that is, this became a chapter in topology after Witten pointed out how you could get non-invariance out of the holonomy. So in Witten's setup, here's our familiar line element without a time element. It's a purely spatial vector potential kind of element, where the AIs are matrices, non-commuting with one another, written in terms of some basis, perhaps. And the holonomy we're interested in, the path that we're interested in, is a knotted loop. You start at the beginning of the path, you parallel translate all the way around the path and come back to where you started, and measure the difference that happened. And you can measure the difference that happened by thinking about the linear transformation that's produced by parallel translating and then taking the trace of that. And that gives you a measure called the Wilson line of this holonomy. And that will be directly related to the curvature, the dA plus A wedge A, if the loop is very tiny. But if the loop is global, then something about the topology of that loop is being reflected by this holonomy, a kind of big generalization of a Hronoff-Bohm in its way. And Witten understood that this holonomy in and of itself is not a knot invariant, because after all, if we bumped it a little bit, just made a little change in it, why, then the whole thing would change in relation to the curvature of the field. As we said, a tiny loop gives us the curvature at a point. It gives us the field strengths at the point. And so what to do? Well, if you could average it in the right way so that you would wipe out that curvature behavior and just get down to the topology, you would find something topological about the loop coming out of the holonomy. And Witten found the correct way to average it. He averages it over all the fields with respect to what's called the Chern-Simons form. And we aren't going to write that down, but the Chern-Simons form's variation with respect to A also gives the curvature of the field. So these two balance one another out, and the integral ends up being a topological invariant, if it existed. But it exists formally, and it can be analyzed as to how it behaves. It can be perturbatively expanded, and one gets formulas of a more particular and detailed nature about these invariants. And many facts about the invariants are directly readable from this integral and its meanings, even though the measure theory has not yet been constructed for it. And presumably sooner or later, that part of the story will fill itself in. So here, the conjectural mathematical physics rides ahead of the rigorous mathematics, but other models that fit all this that are rigorous were constructed. And so Hermann Weyl's idea of that line element goes all the way through up into this topology. And that's quite fascinating. And that in itself could be the end of this talk. But I wanted to go on and talk about how derivatives written as commutators are interesting and give some insight into the way things are built. So let's go back to and add time to our remarks about calculus. We peculiarly did calculus without mentioning time, which is ahistorical, but let's do discrete calculus with a delta t. That dt in there is a delta t, it's not an infinitesimal. So I take x prime to be the value of x at the next time minus x, and divide by dt, delta x over delta t. And I want to know what happens to this discrete differentiation process if I'm thinking of this clock ticking and time is going forward. And I want to do different operations. I would like to observe the velocity. And observing the velocity, that is computing x dot, that requires the clock to tick. And so when I then observe x, I have to observe it at the next time. On the other hand, if I observe x, it does not require the clock to tick. So I will be a logician in this form and say, therefore, I shall not have the clock tick. But when I do the x dot, the clock must tick. So then I would get x, and then I would get the delta x. So you see, it's written below that if I first, and the order of operations is from right to left. So if I first find the velocity, then my next find the position, and it's at the next time. If I first find the position and then I find the velocity, then the velocity is computed just fine, but the position was at the original time. And there's a commutator to examine the position velocity minus velocity position commutator, and that is equal to the delta x squared divided by delta t. So you see, that's a basic commutator in a discrete world of where there's a time series and you're looking at the difference between position and momentum, and position and momentum don't commute. No one is claiming this is quantum mechanics, but it's worth comparing with physics nonetheless. We have this, and we could say, if I were to take the constant to be delta x squared divided by delta t and look at commutator equal to a constant, then I could solve it by saying that x prime will be x randomly plus or minus delta x. That will solve this and work out exactly as I just indicated. So the discrete analog of Heisenberg's equation yields a Brownian walk with diffusion constant k. And I do call delta x squared over delta t the diffusion constant, because length squared over time is the dimensions of the diffusion constant in a Brownian walk, in a Brownian process. And while this is a digression within a digression, I think it's worth reminding us of that, but also reminding us that we can make everything work in terms of commutators, as I said before, by putting in a j if I wish, right? So I could say, I'll do it this way. I have x dot is jk, all right? And then I have x prime minus x squared over tau is equal to k. We'll solve that equation. And I have a Brownian walk with step square root of k tau. and k is delta squared over tau. Just like that. And on the other hand, why do I say that's the diffusion constant? I just want to point that out to you, because you see, you go a different route when you think classically about this, the way people usually do. You say x at time t plus tau is x at time t plus or minus delta, the step. And then what's the probability of being at t plus tau, assuming that you flip a coin for the plus or minus? Then you have probability 1/2 of stepping back, and probability 1/2 of stepping forward, and you get a difference equation. And then you stare at this difference equation and say to yourself, well, how could I make it into a differential equation? Well, for the probability, well, I could subtract the appropriate thing and play with it, and I find that it turns into dp dt equals some constant times d squared p dx squared. And the constant is that diffusion constant. It's step size squared divided by tau, maybe times 1/2. So that's the usual source of the diffusion constant. And then if you were going to go to quantum mechanics, which this is just a hint in another direction before I go getting a little more detailed, you could put an I in there. I put an I in there in the same way that I would say that Schrodinger's equation is this equation if I put an I here. If I write dp dt is I d squared p dx squared, then it becomes Schrodinger's equation. And then our process becomes steps with imaginary steps. And you can think about that if you want. But now let's get all too general. So I want to work in an algebra where I have commutators. That's all. So I'm imagining a very strange advanced calculus course where we're going to do all our derivatives with commutators, and maybe we aren't implying any physics at the beginning. So given an element n, I have a derivative in the direction n, I'll say, which means take the commutator with n. And I have the Leibniz rule. And I also have the Jacobi identity, of course, because that's a fact of life about commutators. And the Jacobi identity is going to tell me the following nice thing, that if I were to take two derivatives, delta I and delta j, each one represented by an n sub I, take the commutator with n sub I, or take the commutator with n sub j, and I take the commutator of the derivatives, which is what I want to do if I'm going to think about curvature eventually, then it's the same as taking the commutator with ni, commutator nj. So commutator of operators becomes commutators of the entities that represent those operators. And the reason why this equation is true is the identity of Jacobi. And in the interest of time, we won't do the algebra. So then I could have a non-commutative world with lots of non-commuting derivatives, and I could denote them by delta sub a or delta or f colon a in the usual ways. And I can define my elements of curvature to be the Rij's, which are the commutators of the guys that represent these derivatives. So that would be my beginnings of calculus. And then you will find that some things you're familiar with come out because of the Jacobi identity. It's as though all you have is the Jacobi identity in this world. The Jacobi identity says ABC, CAB, BCA, and this represents a curvature RAB taking its derivative in the C direction, curvature RCA taking its derivative in the B direction, curvature RBC taking its derivative in the A direction, and that's called the Bianchi identity in differential geometry. It's the Jacobi identity here. So now, watching our time a little, let's do advanced calculus. And let's do advanced calculus first, similar to Feynman's setup, by beginning where the derivatives are going to commute with one another completely. So this is even simpler than Feynman's setup. So I'm going to have p's, which commute with one another. And that means that the derivatives that they represent will commute with one another. I'm going to have p's that delta ij the x's so that the pj's represent derivative with respect to xj. So the derivative of f with respect to xi is the commutator of f with respect to p. But this goes symmetrically delta ij. So I can also say that the derivative of f with respect to pi is the commutator of xi with f. That's just the symmetry of this. And then I should have time. And so I will designate an h and call it the Hamiltonian with malice aforethought and say that the time derivative of f will be the commutator of f with h. Of course, if we were doing quantum mechanics, we'd have to add an I there. Well, then, one of the remarkable tautologies of this setup. Now, mind you, all we have done is created advanced calculus, right? We want our derivatives to commute with one another, and we want to have lots of partial derivatives. And we want to have some coordinates that are commuting with one another. So we're formulating advanced calculus in a non-commutative context, and we have time. And then I say Hamilton's equations are a tautology here. Here they are. The derivative of pi with respect to t is the commutator of pi with h by definition. And that's the negative of h commutator pi, and that is the negative of dh dxi. On the other hand, the derivative of xi with respect to t is the commutator of xi with h, which is the derivative of h with respect to pi. Remember our duality, and that duality is why we have the plus and minus signs here, and these are Hamilton's equations of motion. Of course, there's no physics here yet. All the physics is in the Hamiltonian. If you choose the Hamiltonian in the right way, it'll turn into some physics. But here it's a tautology of the idea of representing everything by commutators. And of course, historically, you can see where this tautology comes from historically, because Hamilton got the commutators, albeit by an indirect method, right? Hamilton said first, probably, the Hamiltonian is given by p squared over 2m plus a potential, and we have Newton's law, and you put these things together and out comes Hamilton's equations. But then given that you have Hamilton's equations, Q is the position, of course. Given that you have Hamilton's equations, then you can look at the time derivative, and the time derivative is given by dfdq q dot plus dfdp p dot. That is fundamental advanced calculus. But then the q dot and the p dot can be replaced by derivatives of h, and then you get that the time derivative of f is equal to the Poisson bracket of f with h. I'm walking backwards into the history of it. And so you see, you should define the Poisson bracket, and then, of course, it was found by those people back then that this satisfies the Jacobsi identity also and is highly analogous to a commutator in the abstract sense. And then moving forward in time from the 1800s to Dirac, Dirac realizes that the transition from classical mechanics to quantum mechanics should be the replacement of the Poisson bracket by an I times a commutator. And that brings us full circle in this circle of ideas. And I have gone backwards and said, well, let's start with the commutators and see what are the formal properties of just doing the calculus using the commutators, and we walk into Hamilton's equations first rather than later, and the connections with the physics can then be looked at all over again. It's quite amusing. I'll skip this one. By the same token, the gauge field forms are coming out here. Just consider looking at the grand generalization that should be right in front of you of what would a physical law look like. There should be some expression of the rate of change of the position variables with respect to time, which is given by commutator with h, if you want it, equal to some elements GI, which depend on the physics or depend on the dynamics that you've chosen. So there's some collection of elements in the non-commutative world that describe the rate of change of the point with respect to time. And we're going to write those GIs in relation to the original momentum representatives PI. And of course, that's with malice aforethought too, because writing things in that form took a while for people to realize that's a good thing to do. But if you write it that way, then the AIs become the analogs of our potentials again. And we have that the curvatures associated with these GIs, the way those derivatives defined by the GIs do not commute with one another, is given by the commutator of PI minus AI with PJ minus AJ. And now you see, there it is. There's the formula. In this case, the formula is coming out directly out of commutators, just as it would if you were doing covariant derivatives, and you didn't have to add it on as an extra term in the differential form. So there's the formula for the curvature of the gauge connection coming out of a general idea of what a law of motion would be. And then I want to convince you that a good Hamiltonian to choose is one that has a quadratic form like this, where the coefficients in the Hamiltonian are some GIJs, which I can imagine to be like metric coefficients. And I can calculate from this that the xi dot, which was the important term in Feynman's original setup, is now Gij rather than delta ij. Why do I say these things? Well, first of all, you should remember that in the usual metric form, you say ds squared is Gij, dxi, dxj. So ds squared dt squared is Gij, dxi, dt, dxj, dt, is Gij, pi, pj. So you see, it makes sense to think of the Hamiltonian as being given by Gij, pi, pj. So quadratic Hamiltonian is the classical idea, really. And then you can verify that if you choose a quadratic Hamiltonian, and then you'll notice that I'm symmetrizing. And sometimes I have to be very careful about symmetrizing because I'm working non-commutatively. If I symmetrize and take f dot to be f comma h, f commutator h, then the xi dot will be the Gij. So I have a relationship between those metric coefficients and the xi dot, the covariant derivative of the xi in the xj direction with respect to that velocity. And also what happens is that if you choose the h that way, then in the non-commutative world, the classical derivative with respect to time behaves correctly. That is, it's the derivative with respect to the xi's times their dots, exactly as you would hope. You really need a quadratic Hamiltonian in order for the commutative and non-commutative worlds to fit one another at that derivative level of time. We call that a constraint. That's the first constraint. And if you ask for higher order constraints, then the story gets more interesting, and I won't try to talk about that here. So this is a summary of where we are so far. And then I just want to tell you one more bit of the story, which we're going to truncate, and that is the appearance of a Levi-Civita connection. We have the GIJs given by commutators, and I tell you that if I use xj dot for my derivatives, so commutator with xj dot is delta j, nabla j. Nabla j is a covariant derivative given by that. And then define this analog of the Levi-Civita connection. Then it is obtained by taking derivatives backwards from the acceleration. Now, there are two things that are interesting about this. You usually think of the Levi-Civita connection as being obtained by asking for angles to be preserved under parallel translation. Here, I'm getting it out of the acceleration. And I'm doing it by sort of taking antiderivatives in the sense that I'm taking derivatives with respect to pi, which means taking the commutator with respect to xi. But then when you do that, you find that what you're really doing is repeating the Jacobsi identity in various patterns that give rise to the Levi-Civita connection. So underneath the pattern of the Levi-Civita connection is the Jacobsi identity. These are things that only a mathematician can love, maybe, but I like the fact that I can see that inside of one mathematical pattern is sitting another in that way, and it gives one food for thought. If you then take that connection and add it to itself, then you see a familiar kind of thing. You see that the sum of the connection with a permutation is given by the derivative of the GIK. And it's the covariant derivative of the GIK, of course. If you put in the standard derivative, that would be the usual Levi-Civita connection. And this deformation of the Levi-Civita connection, interestingly enough, is one of the keystones of Weil's theory that he made for getting his line element to live in general relativity. So it's worth thinking further about what's happening here in regard to that. I think that this is, well, no, let me take a minute and go just a little further for the sake of context. If you play with this a little further, you find that the acceleration is given by that connection times these velocity products, and by these momenta, and the field times these velocities. And this is natural. This fits into the classical way of thinking. And so all this comes around full circle in ways that are quite interesting. I just wanted to give you a hint about what the generalized Feynman-Dyson derivation looks like without doing it. So I'll just show you this and stop. Are we out of time?
Yes, we are a little bit after time, but it is.
Oh, I'm sorry. I thought I was counting 50 minutes. So I'll stop here, but I'll just make a comment. If you follow this procedure, this way of thinking, and use the covariant derivatives, then you can get a little more than Feynman got. You get an electromagnetic picture of a general gauge theory. These are generalized fields. And that's a good place to stop. And I'll stop.
Thank you. Thank you very much for this fascinating talk. And Professor Kaufman, I would like to ask you to look at the question that was asked, because it is the first question that we have is about notation, and I think that it will be better if you look at this rather than.
Yes, I'm not sure where this question occurred. Let's see.
Questions and answers. This is question from Grzegorz Koczan.
Yeah, I have the chat line open.
Yes. Next to chat is question and answers.
Next to chat, on the bottom are questions and answers. And
next to the chat, not in the chat line?
No, I will read it.
Well, my screen doesn't have a, oh, I'm sorry. Thank you. Question is whether the notation, yeah, I'm here. I've got it. The question is whether the notation dx dy for dx wedge dy does not collide with the Fubini integral. I'm perfectly willing to write dx wedge dy for dx dy. I was simply writing it in the simplest form that I could in the non-commutative algebra that I had. Okay, we write dx wedge dy for good reason, because we want to indicate that we're in the non-commutative version. Okay.
Thank you. Thank you. I must say that I was very much interested in your remark, despite you saying that it is only for mathematicians, about those deeper structures connected with Levi-Civita connection. Could you
explain? Well, I wouldn't say it's only for mathematicians, but the mathematician tends to key on something like that because it's purely structural.
So it is purely structural. My intuition is that frequently in physics, when we see some mathematical structure, we sometimes can interpret and find its deeper meaning in physics. Of course, I don't know
I agree.
What would be the
I agree. I was really making a psychological remark. Like you can imagine Hermann Weyl having been so fascinated, being one of the originators of using differential forms, and then seeing electromagnetism falling into such a beautiful pattern, he was absolutely convinced that it had physics in back of it, right? And he was right.
Yes, yes, of course. Are there any other questions? I encourage participants to type their questions and send it, because we still have 10 minutes for the discussion. Our organizers asked us to have 20 minutes for discussion, but I think that it was right that Professor Kaufmann's talk was a bit longer, yet still we have some time for questions.
Yeah. I have a question.
Yes, please.
It seems like we lost the knot theory. All of a sudden, there was not much talk about the knot theory. Where did the knot theory go?
Oh, no, well, the knot theory goes in a very large number of directions. First of all, what I didn't mention was the history of that. The history of that goes like this. Von Jones found a new invariant of knots around 1983, which was capable of detecting mirror images in a way that had not been seen before, polynomial invariant. And it was obviously closely related to statistical physics because of the way Von had discovered it through its relations with the Temperley-Lieb algebra. And Atiyah asked Witten and other people, shouldn't there be a quantum field theory interpretation of this invariant? And Witten was sagacious enough to give a correct answer to that question. That answer is the one I wrote down. So at that point, there had been very big relationships with statistical mechanics. Many new invariants had been discovered by using the idea of the relationship with statistical mechanics, because the basic core of constructing these invariants combinatorially comes from solutions to the Yang-Baxter equation, which were discovered by statistical mechanics people early on. And then Witten pointed out that it was indeed related to holonomy in quantum field theory in that sense, and that meant that there were also three manifold invariants, and then around the same time, Turayev and Reshetikin found ways to write the three manifold invariants using more algebra and less quantum field theory. And there's this big efflorescence of all sorts of knot theory invariants, some of which led to the proofs of conjectures that had not been solved before, and some of which led to brand new invariants via ideas related, for example, to the perturbation expansion of the integral. And then this continues to this day, where people have discovered even stranger things, cohomology theories that are related to the links that give rise to these invariants as special cases, in the same way that the Euler characteristic of homology that gives rise to the Betti numbers. And the field is very large. And there's a sub piece of it that I forgot to mention the name of, called topological quantum field theory, which is the abstraction of Witten's idea of using quantum field theory for topological problems. So there's really a very large development there.
May I? Do I have a few seconds for a question? Yes, Professor Kammerer. Yes. Professor Kammerer, I've been very intrigued and interested in your what I call the D quotation mark calculus. However, my knowledge of the field at this moment is quite minimal. So with your permission, I would like to write you a message tomorrow. The issue is the following. Due to its intriguing connection with the commutator, whether this beautiful D calculus can be extended in such a way to represent the extended character of hadrons. Because once this is done, then you automatically have realization of Bohm hidden variables. You have exact representation of nuclear magnetic moments and other possibilities. So if you don't mind, I don't want to abuse your time. Tomorrow I will write you a little very informal letter.
Oh, please send me a note. We can correspond on it, certainly.
Thank you. With understanding, however, that I'm not terrible, but I hope you will send me some paper that I can study, so the next time I can be more meaningful. Thank you.
Yes, sure, of course. I wanted to get back to the question about dx dy. All I'm saying is it was an initial notion to just write dx dy. We can certainly adopt dx wedge dy to make the right distinctions. Okay. Oh, sorry, I misspelled distinction, but that I hope that makes the answer to my question, to that question, understandable. In what I was doing, I was not doing differential forms later on. My dx dy's were not anti-commuting dx dy's later on. I was talking about motivating differential forms in the earlier part. And then you do, just in ordinary calculus, you need to write dx wedge dy to let the person know that you are talking about non-commutative algebra there. Sure. It's similar to the problem with the square zero infinitesimals. Those people want the epistemology that zero is indistinguishable from the square zero infinitesimal, but they better have a different notation for it, or else you're going to be writing zero and thinking of it sometimes as an infinitesimal and sometimes not, which doesn't work either.
Thank you. Thank you very much for a fascinating talk. And I hope that your discussion with some of the participants will continue. I hope that we will, in general, have many discussions which will be starting from the talks presented at this conference. Please don't allow me to finish. Because yes, I would like to announce our next speaker, Dr. Carlos Cesar Jamir Jimenez, who will be talking about philosophical honoring of quantum natural language processing. Fascinating and for some of us definitely exotic topic. So please, you have the floor.
Thank you very much. Well, first, I could say that I feel honored of being able to share with you my thoughts on some of these issues. And I could say that I wouldn't be interested in these topics if it weren't because of Dr. Zbigniew Osiewicz. He was the one who introduces me to category theory, and that's the way I started to think about language many years ago, but thanks to him. So this is going to be a very introductory talk. I will share my screen in a few minutes. And the remark that I want to make is that we do not need sometimes very complex ideas, but elegant ideas in order to have deep understanding of some phenomena. And I guess that sometimes what happens with language is so close to us that sometimes we do not know how to handle it from a theoretical point of view. So this is going to be a group of philosophical remarks, and there are going to be some technical aspects, but they are to the very minimum, okay? So I will share now my screen. Okay. So I guess that now you should be watching my screen. And well, this is a talk on this model that has been called by people from Oxford University and Cambridge University, Quantum Natural Language Processing, or QNLP. Basically, this is the work of people led by Robert Cook in United Kingdom. So I would talk about this. And the plan of my talk is very simple. I will have only three points to make. First, I will explain quite briefly what is QNLP, which are some of its remarkable traits, and then then some challenges. What are the challenges that we have if we adopt this framework and if we want to broaden its scope? When I'm talking about broadening the scope of this framework, I'm referring to going beyond the sentence. Something that is quite interesting about this framework is that they were able to manage some compositional methodologies from word to sentence level. But the next challenge would be to move from sentence level to the text level, or even to the discourse level. And well, that requires another kind of conceptual apparatus in order to work properly. So let's start with the first point. That is very simple. What is quantum natural language processing? Well, quantum natural language processing is a canonical implementation on quantum hardware of a compositional treatment of the semantics of natural language expressions. And I'm saying that this is related to the semantics, because as we know, natural language, or what we call natural language, has a lot of levels of structure. We can talk about the sounds, we can talk about the syntax and different features. But especially we are concerned with the semantics, with the meaning. Obviously, meaning cannot be disconnected from syntax, or cannot be disconnected from patterns of sound, such as intonation or stress or something like that. But the main point here is the semantics, not the phonetic features or the syntactic features at the sentential level. And this is a canonical implementation on quantum hardware, matching the way quantum systems compose. According to the people who has worked with this development, they think that the way in which quantum systems in nature somehow can somehow mirror the way expressions are built in natural language, or well, it's not clear whether one mirrors the other. It's not clear if we're talking about an egg and the hen problem here. But anyway, the thing is that there is some way of natural implementation that can be done. I will go further into this issue. What are some of the remarkable traits of this framework? Well, quantum natural processing of language is based on another mathematical framework that has been named DiscoCat, that is a categorical, compositional, distributional model of meaning. This model was developed in 2010 by these authors. And the idea here is that this approach, this DiscoCat, unifies two approaches to natural language processing. Basically, the distributional theory of meaning in terms of vector space model and the compositional theory of grammatical types. Well, this distributional theory of meaning in terms of vector space model somehow associates words with vectors. The idea is that we build some meaning spaces and we can somehow calculate how far one word is to another in the same way in which, how far the meaning of one word is to another in the same way in which we calculate the distance between vectors. And the basis of our vector space are going to be all the words that form the context in which certain words occur. What this implies is that we will have very high dimensional vector spaces, and dealing with these high dimensional meaning spaces is really a computing problem. In this way, that's why these people think that quantum computing could be really helpful in these issues. But well, that has to do with the distributional theory of meaning. I will talk a little bit more about this. And then we have the compositional theory of grammatical types. And the framework that these authors are using is basically the work done by Joachim Landeck regarding pre-group grammars. And well, this is not the only framework that could be used. We know, for example, from people who work in linguistics, that certain grammatical types are composed of some basic types. For instance, if I think about a noun phrase, the type of a noun phrase can be built from some other basic types. For example, by a noun and by an article. For instance, if I say the cat is a noun phrase, and this is composed of other two types. And obviously, well, this is just a simple example. We can have noun phrases, but there are much more complex phrases, or much more complex structures, prepositional phrases, relative clauses, and all of these types, these grammatical types, have a very subtle structure. And sometimes the traditional grammar does not capture all these subtleties. For instance, I have always been very critical of how the way we work with words such as adverbs. And I cannot understand why in some books, some people think that the word very, like when you say, I am very happy to be here, belongs to the same category than the word slowly, like I am eating slowly. So how come do you think that slowly and very can have the same grammatical type? This doesn't make sense to me, because if you have a much more complex theory, you realize that the role that each of these particles play in sentences and in the semantic building of messages and communication is completely different. So the traditional grammar is not enough to grasp all these issues. But well, so well, this is what I was telling you. For instance, the first approach that is unified in this framework, the distributional theory of meaning, is related to vectors. For example, we can, if we think of words such as cat and dog, we know that these two words might be very, very much more similar to a word such an account. Yeah, if you think about account and money, then maybe account and money might be very similar, but that's not the case with words such as pet and cat. However, if we think of some other words that are close to these expressions, for instance, if we think about cat, we know that it's very common to find the word milk when you have a sentence where there is the word cat. It's very common that you have milk, or for example, that you can have the adjective cute, or sometimes you can have the word dog, but it's not so common to find in just one sentence the word bank and the word cat, right? And well, so this is the distributional theory of meaning. Now going to the compositional theory of grammatical types, and this is where category theory has a lot to say. Well, wait a minute. Let me see. Okay. In this case, for example, we know that having a sentence such as Romeo loves Juliet is not the same as just having the word Romeo and the word loves and the love Juliet. I mean, there is a sentence is not just a bag with words, yeah? There is some structure involved. So the meaning of a sentence, if we can think about that, requires some particles, but also it requires some compositional rules in order to derive the main meaning. So wait a minute, let me just check something here. Okay, now, but this is regarding the grammar types. Something that a lot of linguists and philosophers have been working on for several years is logical semantics. Logical semantics is compositional too, and this can be, for instance, modeled using category theory. For instance, we can have, in terms of morphisms, a sentence like Juliet snores. In this, if you look at the graph on the left, we can have, for instance, the morphism Juliet, that is a morphism that peaks from the, let's say, the set P, the set of people, picks one woman that is Juliet, and then we can define, for example, a predicate that goes from the object P, that is the group of people, to an object of truth values, omega. This object of truth values will help us to tell whether somebody in the set P snores or not snores. Yeah, if Juliet snores, then the composition of those two morphisms will be mapped to true, and if Juliet does not snore, the composition of those two morphisms will be mapped to false. Yeah, so this is a way in which we can have a compositional model of the way sentences are built. But also we can have truth conditions. This is quite important. Sometimes if we only work with grammar, we might not have truth conditions. And if you do not have truth condition, in my opinion, you do not have semantics. And well, this issue that I'm raising, the difference between logical semantics and compositional type grammar is important, because in categorical terms, the model on the left will require another category that somehow will model the objects we are talking about. Somehow it's going to be an ontology, while the model on the right, the one that is only concerned with grammar, will give us some syntactic structure that is quite important, but it's not going to give us truth conditions. However, that structure is going to be relevant. So let's go on, and I will give an example of some of the remarkable traits that DiscoCat help us understand. For instance, I have here two sentences. The dog is on the table and the cat is on the table. We can realize that these two sentences are very similar from a syntactical point of view. But also we will like to know whether these two sentences are close in meaning or not. Our intuition is that they are very close in meaning, because the only small difference is that we have there the word dog and the word cat. The categorical distributional compositional model is able to quantify the distance between these two sentences. This is something that cannot be somehow modeled with very traditional truth conditional models that are just extensional, because if in the very traditional compositional models, the logical models, these sentences are just true or false. You say the dog is on the table, well, that's true. The cat is on the table, well, that's true. And so there is no way in which you can notice that difference from the model, right? You only can see that you have two true sentences, but everything is collapsed. Obviously, some philosophers will say, well, the thing is not so simple. We can have, we are not dealing only with truth values. We are concerned with the world. We are concerned with possible worlds. And some philosophers would say, the dog is on the table. The meaning of the sentence, the dog is on the table, is the proposition that somehow denotes a set of possible worlds where the dog is on the table. And the cat is on the table. It means a proposition that somehow denotes all the possible worlds where there is a cat on the table, right? And well, this is a very complex model. But anyway, the meaningful thing here is that the DiscoCat model allows us to quantify on these structures, not only on words, but on the complete sentence. For example, we can have the car is on the street, and this sentence is different from the previous sentences, but somehow we expect this sentence to be close in meaning, but not so close. So the question could be, how far are these sentences from each other? Obviously, well, sorry, I have there 5 centimeters. This doesn't make sense. I mean, it's just a number. We can have arbitrary numbers. The important thing is that numbers are helpful for grasping relations. No, it's not the numbers itself are not the meaningful thing, but the structure of the system that we use to measure. But well, this is something that the model allows us to do. Now, just to go on, then how can we hone the framework and how can we broaden its scope? Here, I will only raise questions. I do not have answers. Well, I have some hints on how to deal with some things, but it's not possible to talk about that in just a few minutes. But well, I will mention four things that need to be taken into account if we want to make this framework much more robust to work with semantics. First, the real challenge of the meaning of logical constants. What is interesting about this framework is that meaning arises somehow from the corpus that is given to a system that is going to process it. So it's not, meaning is not given in a priori way. Yeah, it's not given beforehand. So you obtain meaning from the processing. So a good question is if we will be able to obtain the traditional logical constants. It seems that this is not going to happen, I guess, or at least that we will not be able to make like a map, a simple map from words to logical constants. For instance, thinking about conjunction. A conjunction in natural language can be expressed by several expressions. So I guess that after running some experiments, we will notice, if this is successful, that a cluster of expressions could be mapped to what we normally call a logical constant, whether it is a conjunction or is a disjunction or something. And something else that we will expect to arise by using this model is that depending on the corpus, logical constants might be somehow different, but not so different. There will be some structures, and this structure will depend on some categorical structure that is underlying our corpus. This is something quite interesting, and there is a research line that we can follow here. Then another point, discursive structures, dependent types might be needed here. And I'm thinking about structures such as pronouns, possessive adjectives. All these devices usually link sentences, but we do not only have words, we also have expressions. For instance, as I have mentioned, noun phrases. When you are telling a story and you say, a man was walking on the park, the man was wearing a dark suit. If you have a structure like that, the phrase the man somehow is referring to the first noun phrase, a man that is walking in the park. So all of these syntactic structures and semantic procedures have to be mapped somehow in our mathematical model. And I guess that this should arise as dependent types. And I think that all the work that has been done on type theory that is mapped to different categories will be quite relevant here. So this is also another research line that that we can follow. Another important point is related to belief and meaning. Since the 70s, some philosophers such as Donald Davidson has shown us that when we are stating something, we state something not just because we think that it is true, but also because of what we think the words mean. So there is an entanglement between belief and meaning. Sometimes when we are having a discussion, we do not agree, but sometimes it's not clear whether we are not agreeing because we are ascribing different truth values to our sentences or because we are using the words in a different way. So this is a feature of language. There is not a solution beforehand, but our mathematical model should be able to show up this entanglement of belief and meaning. And another important thing that I guess a model should meet is the challenge of the dynamic effects that we have in a text. For instance, in literature, we can have exactly the same sentence in a novel at the beginning of the chapter and the same sentence at the end of the chapter. But these sentences might not mean the same because of the place they have in this. Okay, I'm
just a reminder.
Good.
Please come. We have still more than 5 minutes for discussion, but please go. Be aware and go to the end.
Okay, very good. Yeah. I'm finishing with that. So this is the last issue. The the differences in meaning that one and the same sentence, but well, it's not clear if it is one and the same sentence. If one of the same sentence in terms of token will have at the beginning of a text and at the end of the text. If we are reading a story, we know that sometimes we, as readers, we realize that the sentence means something completely different if it is placed at the end of the sentence or if it is placed at the end of the text, in the middle of the text, or at the beginning. And our model should be able to work with that. Basically, so that's all for me. So these are just questions that I'm raising, and I think that this can be answered with category theory and with philosophy and linguistics. So it's an interdisciplinary approach. These are the kind of things that I guess that Professor Zbigniew Owsiewicz liked a lot, and I hope that some of you might be interested in pursuing some of these research lines. Thank you very much. This is my email, and I also have the references if you want to check it later on. Okay, thank you very much. That's it.
Thank you for this very stimulating talk. If I may, I would like to ask already signalize a question. I was very much interested by this, by what you stated, that the meanings could be translated into a vector space. And for sure, it is very interesting area of research, but I see immediately one difficulty, specifically how such vector space would change between different natural languages. We know that in every language, the meaning, there is no one-to-one exact map of the meaning between the languages. And in each natural language, words have the meaning a bit associated with its synonyms. The groups of synonyms are different. So let me formulate this question. Maybe let me give an example. That, for example, in Polish language, which is my native, exactly the same word means color blue, means heavenly in the sense of fate, of like Heavenly Father, and means astronomical in sense of astronomical bodies and planets. And in minds of native speakers, those three meanings of the word are, of course, it is used in different contexts, but they are deeply connected. Let me just give a note from my childhood. When I was a child, I drew a portrait of Nicolaus Copernicus, and then my mother asked me, why have you used only the blue crayon? And for me, it was obvious. He was working on the astronomical bodies. It means on blue bodies, it means his portrait needs to be blue. So it is as children sometimes express more directly how the native speakers somehow have all those associations when word has different meanings and different connotation. How could it be translated to the vector or logical space?
Well, I could say that this is quite interesting about a framework, because there won't be a one-to-one translation. That is going to be impossible. What we will have is that we will have different categories, and somehow the map, some information might be lost when you are going from one category to another. And sometimes if you map to a third category, you will be able to grasp some of this information that is lost. And this is This is a good aspect of the model. The model should lose information somehow. It means that it is working properly. It means that you need some extra categories to map these differences. So I guess that's right, that is going to happen. And the only way to overcome that is to have like a third category. If you have only two languages, you will never catch this difference. You need at least a third category to start distinguishing between one and another.
Yes, thank you. This is very interesting explanation. I totally agree. Thank you very much. Now we need to come to our next speaker. There's another question. Let me read it, please. Bond and Romero define meaning as a pair R as a function of S, X as a function of S of X, where R is the class of reference concept and S is the sense. The formalization allows to compute things as vaguely, This is the question for Maria Espinosa Aldama.
I'm not sure what is the question.
And the next question is for you to share the references.
Yeah, I will share the references. I will paste the references on the chat. And thank you very much, Mariana. Yeah, it makes sense what you are saying. This reference by Bunge and Romero. I will copy the references on the chat. Thank you.
Thank you very much for this interesting and thought-stimulating talk. And our next speaker is Miguel Perez Gaspar and Everardo Barcenas. Robert, maybe you announce. If you,
Hola.
Sorry if I.
Can you hear me?
The title is sobre
Yes.
independencia axiomática de una lógica transvaluada.
Okay, give me a second for display my presentation.
Yes, please.
Okay. Hola, mi nombre es Miguel Pérez Gaspar. Esta plática va a ser dada en español como una forma de incentivar a todos los posibles estudiantes interesados en el tema de lógica 3 valorada. Multivalued logics is this topic. Okay. Este trabajo lo consideramos un work in progress, aún está siendo trabajado, pero tenemos algunos resultados importantes dentro de la misma área que nos gustaría compartir con ustedes. Estos son nuestros correos electrónicos. This is our emails. If you have any question for us, is welcome, okay? Tabla de contenido. Voy a hablar de una pequeña introducción. Voy a hablar un poco de este principio, ex contradicción could leave it. Voy a hablar de la historia moderna de las lógicas paraconsistentes. Voy a presentarles específicamente una lógica paraconsistente llamada CG3', una primera axiomatización tipo Hilbert y voy a hablar de la independencia. Esta es la parte fundamental, is the main point, donde voy a hablar acerca de los resultados de nuestro trabajo y un poco de la bibliografía. Introducción. ¿Qué es la paraconsistencia? Una lógica es paraconsistente si y solo si su relación de consecuencia semántica o de teoría de prueba no es explosiva. La paraconsistencia es una propiedad de una relación de consecuencia. El argumento ex contradiction could leave it es paraconsistentemente inválido. En general, no se da el caso de que una fórmula y su negación deduzcan a una segunda fórmula psi. El principio de explosión, así es también como se llama esta partícula, este principio, es una ley de la lógica clásica, la lógica intuicionista y otros sistemas lógicos, según el cual cualquier oración puede ser demostrada de una contradicción. Es decir, una vez que se ha afirmado una contradicción, se puede inferir de ella cualquier proposición, incluidas sus negaciones. Esto se le conoce como una deducción deductiva. Considere las siguientes oraciones contradictorias. Todos los limones son amarillos. No todos los limones son amarillos. La conclusión. Entonces, los unicornios existen. Este es un ejemplo de ese tipo de deducciones que se dan en estos tipos de sistemas. Voy a hablar un poco de la historia moderna de las lógicas paraconsistentes. Las primeras lógicas paraconsistentes en la era contemporánea parecen haber sido dadas por dos rusos. En 1910, Vasiliev propuso una silogística aristotélica modificada que incluye declaraciones de la forma S es a la vez P y no P. En 1929, Orlov dio la primera axiomatización de la lógica relevante, R, que es paraconsistente. Bueno, dentro de estos trabajos, ninguno tuvo un impacto en ese momento. El primer lógico formal que desarrolló una lógica paraconsistente fue Jacobsi, en Polonia, que era estudiante de Lukasiewicz, quien él mismo había previsto una lógica paraconsistente. En este artículo llamado Aristoteles, Syllogistic from the Standpoint of Modern Formal Logic. Posteriormente, en 1949, Holden presentó un trabajo sobre la lógica de sinsentido, nonsense. Nuevamente, estos trabajos pasaron desapercibidos. Las lógicas paraconsistentes fueron desarrolladas independientemente en Sudamérica por Florencio Asenjo en 1966 y en 1974 por Newton da Costa. Ambos, sus trabajos fueron sus disertaciones doctorales, con énfasis en aplicaciones matemáticas. Actualmente, un grupo de lógicos ha estado investigando continuamente la lógica paraconsistente, especialmente en Campinas y Sao Paulo, Brasil, con un enfoque en las lógicas de inconsistencia formal. Carnielli y Coniglio en 2016 presentan una descripción reciente y exhaustiva de estos trabajos. Bueno, clásicamente existen dos valores de verdad, verdadero y falso. El enfoque de muchos valores es abandonar esta suposición clásica y permitir más de dos valores de verdad. La estrategia más simple es usar tres valores de verdad, verdadero, falso y quizás ambos, verdadero y falso a la vez. Dentro de estos sistemas de lógicas paraconsistentes, en 2018, el doctor Mauricio Osorio de UTLAB presenta una lógica 3 valorada. Esta lógica la denomina CG3', que puede obtenerse mediante una matriz en donde tenemos el conjunto de valores de verdad, 0, 1 y 2. El conjunto de valores designados lo vamos a considerar como aquellos valores que consisten del 1 y el 2. Y nuestras funciones de verdad que consisten de las siguientes tablas. Tenemos la disjunción, implication, implicación, conjunction, and negation. Observa la forma en la que se modelan estos conectivos. La disyunción es el máximo. La implicación tiene un ligero cambio en el valor 2, 1, 2, 1 es 1. La conjunción es el mínimo y la negación de 0 es 2, la negación del valor intermedio es 2 y la negación del verdadero 2 es 0. ¿Ok? Primera axiomatización. En 2019, el doctor Everardo Bárcenas y yo axiomatizamos esta lógica vía la estrategia de los modelos saturados. En esta estrategia nosotros encontramos nuestra base axiomática con 12 fórmulas. Los primeros 8 son la parte positiva de lógica intuicionista. El axioma 9 es alfa implica beta o alfa. El axioma 10, el tercero excluido. El weak explosion es el axioma 11. Y este nuevo axioma, bola de alfa implica alfa. Y como regla de inferencia, modus ponens. Nuestro interés era saber si este conjunto de axiomas estaba bien definido, si no teníamos redundancia, puesto que robustez y solidez nos decían sí, es correcto, pero aún así nos quedaba la duda si era independiente. Cosas que se satisfacen en esta primera axiomatización. Metateorema de la deducción, prueba por casos y reglas AND. Tenemos robustez. Soundness and completeness es un teorema que se cumple en nuestra lógica. Cualquier teorema, si tú tienes cualquier teorema, entonces es una tautología. La forma en la que construimos los axiomas a partir del lema de la verdad. ¿Cómo se construye? Tú tomas a un homomorfismo que va del conjunto de variables proposicionales al conjunto de valores designados y asociamos lo siguiente. Para cada variable proposicional, P, si P es un elemento de un conjunto saturado y además su bola de P no es parte del conjunto saturado, ambos no son parte del conjunto saturados, entonces damos el valor 0. Por otro lado, si P es un elemento del conjunto saturado y bola de P no es un elemento del saturado, damos 1. Si P es un elemento del saturado y bola de P no es un elemento del saturado, damos un valor 2. Este homomorfismo podemos extenderlo a todo el lenguaje. Lo extendemos a todo el conjunto de fórmulas bien formadas. Y por lo tanto tenemos completitud. Cualquier tautología, si tú tienes cualquier tautología, entonces esa tautología es un teorema. Independencia. Dentro de los primeros pasos que dimos dentro de la independencia fue observar que el axioma 9 y el axioma 12 pueden ser demostrados a partir de un conjunto de axiomas más pequeño, a partir de 10 axiomas. Entonces, demostramos bola de alfa implica alfa, que es el axioma 9, y alfa implica beta o alfa. Decidimos seguir la estrategia de Elliot Mendelssohn, de este libro muy conocido de lógica, en donde encontramos una primera definición de un conjunto de axiomas independiente. La definición es la siguiente. Un subconjunto Y del conjunto de axiomas de una teoría se dice que es independiente si alguna fórmula bien formada en Y no puede demostrarse mediante las reglas de inferencia del conjunto de axiomas que no están en Y. Nuestra primera definición. Entonces, nosotros proponemos una nueva axiomatización con únicamente 10 axiomas, en donde podemos observar que los axiomas que teníamos anteriormente podían ser demostrados a partir de esta base axiomática de 10 axiomas. Y seguimos teniendo modus ponens como única regla de inferencia. Bueno, pero aún no tenemos algo que nos diga si estos 10 axiomas son independientes. Entonces, decidimos seguir la metodología que el mismo Elliot Mendelssohn propone en su libro. La estrategia la definimos en 5 pasos. Paso 1. Seleccione un número entero positivo n y nombrar a los números que van de 0, 1 hasta n como valores de verdad. Y elige un número m tal que m está entre 0 y n. Número 2. Los números que van de 0, 1 hasta m se llaman valores designados. Posteriormente, en el paso 3, tome un número finito de tablas de verdad que representan funciones de conjuntos que van del conjunto 0, 1 a n a la k en 0, 1 hasta n. Esto realmente son funciones que van del dominio al codominio, ¿ok? Para cada tabla de verdad, introduce un signo llamado conectivo correspondiente. ¿Qué estamos haciendo? Estamos definiendo tablas de verdad. Usando estos conectivos y letras proposicionales, podemos construir formas proposicionales. Y cada fórmula proposicional que tenga j letras distintas determinan una función de verdad. Se dice que una forma proposicional cuya función de verdad correspondiente toma solo valores designados es excepcional. Realmente el concepto que podemos pensar en la lógica clásica, en la lógica de dos valores, las fórmulas excepcionales son exactamente las tautologías. ¿Ok? Como un ejemplo. Los números m y n se dice que son las tablas de verdad básicas que definen una lógica de muchos valores. En esencia, ¿qué vamos a hacer? Nuestra lógica tiene 3 valores. Con esta metodología vamos a extenderla a una lógica de 4 valores. Entonces, para probar la independencia del esquema de axioma 1, considere las siguientes tablas. Quiero que observes que nuestra primera tabla de disyunción tiene estos valores 0, 2, en donde el 0 es el valor designado, 0 es el valor verdadero. La implicación se comporta de esta forma. Observen, como yo quiero que se cumpla modus ponens, yo necesito que 0, que implica 0, me dé 0. ¿Ok? Y la negación se comporta de igual forma como en el caso que ya teníamos estudiado. ¿Ok? Bueno. Llamemos a una fórmula que siempre toma el valor 0, según estas tablas, la vamos a llamar selecta. Proposición. Modus ponens preserva selectividad. Número 2. Todas las instancias de los axiomas que van de 2 a 10 son axiomas seleccionados. Por lo tanto, cualquier fórmula derivable que va de A2 a A10 por modus ponens es selecta. Observa esta instancia de axioma 1, A1 que implica 2, que implica A1. Esta instancia de axioma A1 no es selecta bajo las tablas anteriores. La demostración es muy sencilla. Observa, modus ponens preserva selectividad. Si alfa y alfa implica beta son selectas, también beta lo debe de ser. Es lo que les decía, yo requiero que implicación preserve selectitud. Entonces, 0 implica 0, bueno, aquí es conjunción, this connective is conjunction, this is implication. Esta es implicación. Implicación preserva modus ponens bajo este parámetro. Todas las instancias de esquemas de axiomas A2 a A10 son selectas, se sigue inmediatamente de las tablas. Puedes hacer tu tabla de verdad de cada uno de los axiomas y siempre te va a dar el valor 0, son selectas. Para ver que esta instancia de axioma no es selecta, basta considerar una evaluación en donde A1 valga 1 y A2 valga 3. Aquí es A1 y A3. A2, perdón. Corolario. El axioma A1 es independiente de los esquemas anteriores. Pequeña demostración. Suponga que a partir de A1, A2 hasta A10 podemos deducir al axioma 1. Entonces tenemos una derivación del axioma 1 en donde exactamente la última fórmula es el esquema A1. ¿Qué pasa con las fórmulas precedentes? Las fórmulas precedentes pueden ser instancias de axioma de A2 a A10 o se siguen por una instancia de una aplicación de modus ponens. Por la proposición anterior, hemos visto que los axiomas A2 a A12 son selectos. Además, modus ponens preserva la propiedad selecta. Así, el axioma A1 se debe de obtener por una aplicación de modus ponens y por lo tanto, nosotros concluimos que A1 es una fórmula selecta, lo cual es una contradicción. De esta forma, con esta metodología, nosotros podemos construir tablas de cada uno de nuestros axiomas y poder así demostrar la independencia de cada uno. La bibliografía. Referencias. Elliot Mendelssohn, Introduction to Mathematical Logic. Número 2. Osorio, Carballido y Cepeda, Revisiting Z. Pérez Gaspar y Bárcenas, Completeness for the Paraconsistent Logic, CG3' based on Maximal Theories. Graham Priest and Koji, Paraconsistent Logic. Eso es todo de mi parte. This is all for me. Thank you very much for your time.
Thank you very much. We have the first question. Is logical value true, more than true, or half true, 1, 2, as in the logic of Łukasiewicz, or anything else? And this is coming from Grzegorz Kołczan. He doesn't even ask about value for logic. How do you interpret this two or more true?
Bueno, ok. Dentro de la lógica CG3', históricamente, de acuerdo a la escuela brasileña, las lógicas 3 valoradas pueden ser vistas como 1, 1 medio y 0. Nuestra lógica fue definida como 0, 1 y 2. Puede darse entonces esa biyección. En la metodología que nos da Mendelssohn, para probar la independencia de los 3 axiomas clásicos, pasa de una lógica de 2 valores a una lógica de 3 valores. Es un ejercicio que viene en el libro de Mendelssohn y pues es fácil construir las tablas. Nosotros estamos llevando esa técnica a una lógica de 3 valores, que es nuestra lógica, a una lógica de 4 valores, a un sistema de 4 valores para probar nuestra independencia. Ojo, no estoy diciendo que este sistema de 4 valores sea una lógica, solamente es una herramienta para probar la misma independencia.
Thank you. I would also like to ask, if possible, could you give a couple of sentence summary of your talk in English for those of us who are unfortunately not so fluent in Spanish?
I'm sorry, I have network low. Is your voice a few, I don't know, how do you say it, cortada?
Could you is it possible that you give a couple of sentences, very short summary of your talk in English, because some of the audience is not understanding well Spanish?
Oh, okay. First, I'm sorry, my English is a few bad. Then I translate in my mind a few phrases, okay? The paraconsistent logic is a special logic where we have three values, for example, 0, 1, and 2. And this logic models of knowledge representation, where we have some phrases, for example, all the unicorns are beautiful. And we have the moon is made of cheese. Then the conclusion is possible all sentence. For example, Elvis is live, for example. More or less, my answer with the questions.
Thank you. Thank you very much. Your English is very good, very well understood. So thank you for giving this information to us. And are there any other questions to this talk? Please ask. If not, we have 35 minutes break. Before the next talk. As far as if I read everything correctly.
No.
No. Sorry.
No.
Sorry, we still have two talks. I've seen there was this break in. So there is the talk at 2 o'clock. So we have only 5 minutes break.
Sorry, Hannah. May you ask
yes.
Fernando if he has an inconvenience to start at this moment?
Okay. Okay. Could you start now? This is to our next speaker, Fernando
Velasquez
Casada.
Sure, that's can somebody hear me?
Yes, everybody hears you.
Okay, so yeah, of course, that's perfectly fine for me.
You have the floor.
Thank you. So you can you see the slides?
Yes, we can.
Yes, we can see.
Perfect. So thanks everybody for being here online. In particular, thanks to the organizers for organizing this very nice event in honor of Professor Osiewicz. What I'm going to talk about is some topic that I had the opportunity of discussing with Professor Osiewicz around 15 years ago already, when I was a master's student at the University of Mexico. As many of you know, Professor Osiewicz was very interested in category theory. And in fact, at least the conversations that we had, he was always insisting me that category theory should be the fundamental language of mathematics instead of what set theory is nowadays. And fundamentally because category theory makes emphasis on morphisms, on relations between objects, and Professor Osiewicz understood that that was the most important thing to take into account, not look necessarily at the objects, but rather look at the relations that these objects have. But not only that, Professor Osiewicz was also interested in making category theory available for everybody. He wanted people from every different academic level, not only PhD students, masters, bachelors, and so on, but even high school and maybe even education at a lower level, for those students to be able to understand or to see, to be able to learn what category theory is about. And this, what I'm going to talk about is essentially the ideas that he was providing in our conversations, maybe with a little bit of touch of suggestions of mine, in the sense of he wanted to build, to start from a very basic notion, in this case, the case of the notion of a directed graph, and from then build on a stepwise way, little by little, add more complex features until we could reach the basic notions of category theory, category, functor, natural transformation, and so on. And the way that this is done is in two particular ways in what I'm going to present. The first one is, given a graph as we understand it normally is a collection of objects together with some relations, some morphisms over those objects. But we can also think that we might need not only those relations, morphisms over objects, but also morphisms over the morphisms that are relating the objects. That is higher order morphisms. So by doing that, we can extend the notion of a graph and create more and more complex structures. Another way is not looking at adding more and more complex morphisms, but rather to look at the graph
Maybe some problem with the connection.
Yes, I was just thinking if it is only me. So we are waiting for the speaker to come back online.
Yes, we can wait.
It's frozen, so I don't know even if anybody hears me.
Yes, we hear you.
Yes, we can hear you, not problems. The problem was that Fernando disconnected.
Okay, so please continue.
No, it's speaking Jesus Cruz now, no, not Fernando. Fernando was disconnected.
Okay, so we are waiting because he started a bit early, so maybe we'll wait like 5 minutes and hope that he will connect again. I already
yes, I think that 5 minutes is okay, and if not, then we have to start with other opponent.
Yes. Okay. So we are now waiting 5 minutes.
Yeah.
Do we have Peter Rowlands the next speaker now connected?
Yes, I'm here.
Okay, so in 5 minutes, if the speaker cannot connect, would you be able to give your talk, and then after it maybe
yes, I could start then.
Switch the talk. Okay, thank you very much.
We trying to contact Fernando while he resolves his problem connection. Maybe we can start with Professor Peter Rowlands if he is agree.
Yes. Professor Peter Rowlands, please. Please connect. The topic is mathematics and physical meaning in relativistic quantum mechanics. Please, you have the floor. We see your slides, but we don't hear you.
We have mathematical structures, such as symmetry groups, equations, and so on. And often these are just created by reverse engineering with no obvious explanation. So formalisms that work in calculation and phenomenology are not necessarily the ones that lead to insights and understanding of the physics. And I want to start with the Dirac equation, which is the key equation in both relativistic quantum mechanics and quantum field theory. And it must be familiar to many people, that equation. And the thing in that equation is we have 4 gamma terms, which are mutually anticommutative 4x4 matrices, squaring to either the identity matrix or minus the identity matrix. There is another gamma, the 5th gamma, gamma 5, which is needed to complete the algebra. Doesn't appear in the equation. And of these 5 basic units, there are 65 identifiable products, plus and minus values included. And it's in fact a group of order 64 requiring 5 generators, which can be the 5 matrices. These came with Dirac's interpretation, that's why we still use them. And the 4x4 structure does tell us something. It tells us that the equation must have 4 solutions, but they don't appear to have any intrinsic meaning. So why does nature choose these operators? Well, I say maybe it doesn't really choose them. Maybe it chooses something related to them, which can be transformed into them. So there are many other algebraic structures with the same property, which could be used equally well. And these are all Clifford algebras. And many authors have considered Clifford algebra as an alternative to the standard gamma algebra. But can we do it in such a way as we get mathematical insight, physical insight, as well as mathematical simplification? Well, I think there's one of these algebras which has a special physical meaning. And this is because it comes from a physical idea. It's a combined algebra of what I consider to be the 4 fundamental physical parameters: mass, which is the same as mass energy, time, charge, and space. And charge is a 3-component thing with the 3 gauge forces. And this is made up of 8 basic units, in my view: scalar, complex, quaternion, and vector. And there's a symmetry which connects these parameters and explains why they use that, those algebras. If we put them together, we get a group of order 64, and there's the 64 terms. See, the upright blue ones are the vectors, and the slanting red ones are the quaternions, and the black eye is just the scalar, pseudo-scalar complex number.
Are you assuming that you're showing us a notation?
Yeah, that's the notation.
But you were not showing it to us. All we see is the header of your slideshow.
Can't you see it? Can you not see what I've shown?
Yeah. We see only first page.
Can you see my slideshow?
We see
slide.
the title of your slideshow.
You can't actually see the slides.
You have it paused. Your screen sharing is paused.
My screen sharing is paused. How did we do that? What's paused it?
I'm not sure.
Says my screen sharing is paused. Is that what happened to
Resume share.
Fernando?
Resume share.
Yeah, but I don't want that. I want, let's just move this out of the way for a minute. I want to show slideshow.
Okay, now we are seeing the next page.
This way they can see the next.
I'm sorry,
Start from beginning.
there was some issue with my internet connection as you.
Fernando, we give now the turn to Peter Rowland. Then you can continue after.
Okay, of course. My apologies.
Slideshow. Well,
You want slideshow. You need to open that up.
the slideshow. Why isn't it doing the slideshow?
You collapse the ribbon. That's why. From the current slide. Oh, you want
Okay.
to go from current slide or
No,
complete?
I'll go back. It's okay.
Okay, can they see it now?
Now, can you see it now?
Yes, we can see.
Got it paused.
Okay, there's a slideshow apparently was paused. So what you can see there is the 64 elements in this algebra. And the red ones are the quaternions, the blue ones are the vectors. Now I can't actually move it along. Oh, that's better. It moves along that way. Yeah, and this is a second version which shows, it's not a second version, there's a second version. If you look at the first 3 lines of the colored text, you'll see it's a double vector system. So we can do a double vector system instead of a vector quaternion system. It's exactly the same. And this is significant because it suggests that the Dirac algebra is really the algebra of a double space. And it's also a double Pauli matrix algebra, since Clifford algebra vectors are isomorphic to Pauli matrices. Now, Heston has called the Pauli algebra multivariate vector algebra, and he defined a full product between 2 such vectors. And he applied it to the momentum or gamma dot delta term in the Dirac equation and showed that this automatically included spin. So there was already physical meaning in at least one of those. Now, the double space algebra, unlike the gamma algebra, has a clearly visibly physically significance. And we only need a pentat of 5 to generate this algebra, so we don't need all 64 terms because it's a space with 5 generators, a group with 5 generators. But all we need is really dual space. So one space is the space that was familiar to us, observation and measurement, and the other contains everything else. So it's like this physics contains 2 spaces, just one space for space and one space for everything else. And I call that vacuum space, and I do it in red. And it's as though the fermion is the singularity existing on the boundary of these 2 spaces. So if we compactify this information of 2 spaces, notice that we started out with 8 units. We had the 3 red ones and the 3 blue ones plus 1 and I. And this is an example of compacting it into 2 spaces in the first line there. But this lowest state, the 5 that we need to generate the whole algebra could be considered the lowest state, but it's not the most symmetrical, because the most symmetrical would be 2 spaces, IJK, IJK. So the numerous ways of writing out these generators all require distributing the units of one three-dimensional structure among the rest. So there in the first line, you see the 8 units I started with, and then I've redistributed the red ones on among the other 5 units. And essentially this creates us the energy in the first term, momentum in the next 3, and mass in the last one. When I say mass, I mean now rest mass, not mass energy. So one of the spaces retains its symmetry. You can see the blue one retains its symmetry, but the red one loses it. And that's the one associated with charge or vacuum. And so in other words, this is what we consider to be creating a local structure from 4 global parameters. In creating that local structure, we create a broken symmetry in the local structure. And we can match these operators in different forms to the gamma matrices. Lots of ways of doing that. But important, one symmetry observed, the other's broken. So the fact that it's a dual space gives us some sort of insight into many things like the point particle, spin half, Berry phase, Zitterbewegung, vacuum, CPT, and things like that. Because it's from 5 asymmetric generators, it gives us an inkling into the meaning of symmetry breaking in the standard model. Because if you take the standard model, you've got the 3 red operators, and they have a broken symmetry now. And it's a much more powerful and compact formalism for relativistic quantum mechanics, as we will see. Now, people have argued that we have a formalism that works in the gamma matrix, so we do. And if that's all we want, if we only want to do calculations, then that's fine. But it doesn't work in another sense. It doesn't give us the standard model. It doesn't explain anything. It just is and useful for calculation. So the formalism isn't complete if it doesn't explain anything. We have a whole apparatus of mathematical objects for this approach. We've got spinors, primitive idempotents, minimum left ideals, all of that kind of thing. And I don't think any of them are really necessary. The existing formalism doesn't have symmetry. It's just got massive amounts of redundancy and fragmentation. Even if you just do a single free particle, the conventional matrix approach can't generate single solutions. It has 4 separate amplitudes for a single particle, and these have 2 different phases, 2 positive energy, 2 negative, and it mixes up E and M inextricably when they aren't mixed up in that way in nature. And we have terms like px plus ipy and so on, with no counterpart in nature. In addition, we change the momentum energy of space-time signature from plus 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 minus to plus plus minus minus. So we have 2 space-like and 2 time-like components. So I think the gamma matrices cause fragmentation of the equation, mix up energy, momentum, and mass. They take up too much logical space. To actually write the first operator, the differential operator, you need 16 pieces of information. You need a matrix of 16 terms, and you need 4 for the amplitude term. So you need 64 pieces of information for just one operation. They also lack symmetry. There are 5 terms in the equation, but only 4 have a gamma matrix, and yet the algebra has 5 gammas. So what we need to do is defragment, separate the energy, momentum, and mass terms from each other. And then I get that diagram there where the blue, red, and green represent bins on the left, all mixed up, and then on the right, separated out. So we can map algebraic operators onto the equation, for example, in that form. And now a key move, trivial, but very important, is to multiply from the left by j. And this has profound consequences because we end up with an equation like that, which is very similar to the previous equation, except that the mass term now has a j in front as well as an I. And that j is the 5th gamma matrix. We could do it with the gammas if we wanted, but it doesn't tell us as much immediately. And you can see there we've separated out the 3 components of the equation, the energy, momentum, and mass, using quaternion terms, k, I, and j, into separate bins, if you like. Now, The real significance of this, if we try to insert a plane wave solution, let's put a plane wave solution in, then we get, putting that into that equation, we get that solution. And immediately we see something significant, because this A was just an amplitude. We didn't know what it was, but now we know what it has to be. It has to be a multiple of this term, ke plus I, p plus ijm, because otherwise we cannot get 0. It has to be a multiple of that, because that is now a nilpotent. It's a square root of 0. A is a nilpotent. It's also completely explicit. We now know exactly what our free particle wave function looks like. And in fact, it's not just ours. It must have been true anyway, even before we made algebraic operators in the matrices, because the equation has not significantly changed. Now we know, of course, there are 4 solutions, but it's now fairly easy to identify them. We need plus or minus E and plus or minus P. So that's what we get, phase and amplitude terms, 4 phase and amplitude terms, each operated on by the same differential operator. However, that's not a very convenient equation to use, because if you've got 4 phase terms, you've got great difficulties with any sort of calculation. So a good trick now is to swap the variation in the phase terms, plus or minus in the phase terms, for the variation in the operator. And we've got the space to do that because we've got rid of the 4x4 matrices. So that's what we now get. And you see this equation now, set of 4 equations with the 4 solutions, has four different amplitude terms, but only 1 phase term, and 4 different operators which mirror the 4 amplitude terms. And if we wrote the amplitudes in the same notation as we write the operators, they would look the same. So we only need a single, we've got a single phase, so we can do a convenient collapsing of that expression into a single expression like there, plus or minus ke and so on. It's more convenient to multiply it throughout by I, so we get a more convenient way of doing it. And this term, the amplitude, remains a nilpotent, and the expression is just that multiplied by itself is 0. And those 2 expressions could be considered row and column vectors. And by the way, it's a perfect expression of Pauli exclusion, because if you've got an amplitude which is a nilpotent, then you cannot have another amplitude exactly the same, and because it would multiply to 0. And of course, it multiplies out to give us the Einstein relation of energy, momentum, and mass. And the important thing here is that the physics is not in the E, P, and M. Those are just scalar values. The physics is in the operators, in the IK and the I and the vector term and the J. That's where the physics is. The physics is in the algebra, not in the coefficients. And we could reverse our derivation by, instead of deriving that from the Dirac equation, derive the Dirac equation from that. Start with Einstein's expression and just do a canonical quantization of the first bracket. And we could also derive the Klein-Gordon equation in the same way by quantizing both brackets. So now we've just done this for a free particle, but we know that Pauli exclusion isn't unique to free fermions. It works for all fermions. And in fact, that's how we really define it. It's usually not free fermions at all. But now what we need to do is understand what it's really about. We say that all fermionic amplitudes in all states are nilpotent. We say that. We postulate the most general form of a wave function is nilpotent, and we should always seek a nilpotent solution for all problems. It means that we don't even need the Dirac equation. We don't need any equation. All we need is an operator. And that completely, if we write down the operator in that form, it completely determines the phase that provides a nilpotent amplitude. And if we're talking about finding a solution, we mean finding the phase. Now, these E and P, we could replace with differentials, but they don't just need to be ordinary differentials. They could be covariant differentials with gauge terms, or they could be, well, have curvature terms. So we can replace E and P with covariant derivatives and include any number of field or curvature terms after the operators. And so this expression still applies, but obviously the phase term won't be a simple exponential anymore. It'll be something more complicated, but it will still apply. So we can do relativistic quantum mechanics for Fermi in any state subject to any number of interactions simply by defining an operator of that form. And then what we do is we don't take the operator on the wave function, we take it on the phase factor. And we square it, which gives us an amplitude squared, which gives us 0. So we can now see our 4 amplitude states are just 4 creation operators in either this amplitude form or in operator form. And the phase factor is simply an expression of all the possible variations of space and time which are encoded in the creation operators. And once we specify the operators, the whole thing is determined. There's nothing more we can do about it. It's completely fixed. So the Fermi is simply a set of space and time variations. The mass term is purely passive. And it means we can no longer define an isolated system, because the energy conservation will work only over the whole universe, since the E and P terms will be the entire range of Fermi's interactions. So we can reduce the amount of information needed to specify relativistic quantum mechanics to just a 2-term operator. And so the amplitude just becomes a wave function, just becomes an amplitude without a phase factor. If we choose to do that, using discrete differentiation, we can do this if we go over to Luke Kaufman's discrete differentiation. And I'm following his discrete differentiation here for E and P. And here, what we see is very interesting, because we can define our discrete differential in that way, and we can work it out. And what we find is if we generalize to 4 states, then what we see is that the operator doesn't have a mass term. The amplitude has a mass term, the operator doesn't. And that means that we can treat the operator as either having IH bar in front or not. So it could be either classical or quantum, and it's the same equation. It doesn't require it to be specified in advance. We can find the same equation. We can also show that our nilpotent wave function here on the second of these 2 equations is from the same equation as an idempotent, which is the more normal form of this, which is in conventional versions of this type of work. You have an idempotent wave function, but you can see it's just a matter of shuffling one coefficient from the operator to the wave function. There's no change in the physics or mathematics. So the wave function has both properties. So the nilpotent formalism is actually optimized for calculating efficiently, even by comparison with non-relativistic versions of quantum mechanics. It's much easier to do this version of relativistic quantum mechanics than any version of non-relativistic. So reduction to a single phase factor means you can deal with all aspects of a problem in a single calculation. And the extra constraint of nilpotency immediately forces on us an interpretation which connects every Fermi holistically and non-locally with the rest of the universe. So if here I've just done Dirac's prescription for changing to polar coordinates to see what anything would be in a central field. And what we see here is if we use this Dirac prescription, we find that we can't actually get a nilpotent solution unless the E term also has a 1/r term in it. So we can't do it without a Coulomb term. And in fact, we find all interactions between fermions include a Coulomb term, strong and weak as well as electric. So if that's the minimum expression that we can use, and then we can work that one out with the minimum expression to find the Coulomb solution in just 6 lines of calculation. And that to me is the shortest calculation I've ever seen, relativistic or non-relativistic. Now this is well known, but can we do others? Yes, we can do. There are 2 others, and only 2 others. If we got an extra R term, we get a characteristic of the strong interaction, infrared slavery, asymptotic freedom. I haven't included the details here, but I can show them to anyone who wants it. It's already published anyway. And the other one, any other polynomial will give us a harmonic oscillator, which to me is the characteristic of a weak interaction, creation and annihilation of states. We can do an immediate transformation to quantum field theory without needing all the cumbersome apparatus we normally need, quantum field integrals and that kind of thing. And what does it mean? It's actually specifying the interaction between a single fermion and the rest of the universe. If we look at Pauli exclusion again, we've seen that a single nilpotent wave function is automatically Pauli exclusive. But let's do Pauli exclusion in the conventional way using antisymmetric wave functions. And that's what we would get. And the interesting thing is that we get everything cancels except P2 cross P1. In other words, if these 2 objects here have to be different, then the direction of the spin is the only thing that is required to be different in the 2. In other words, the direction of the spin must contain the whole information about any fermion. The instantaneous direction of a spin.
You have 2 minutes more.
Okay. So I'm just going to say what's vacuum. Well, vacuum is, if you imagine plucking out the fermion out of the universe, then what's left is what we would call vacuum. And so we got a difference between local and non-local. What's local? Local is what's inside the bracket. Non-local is what is outside the bracket. A straightforward definition, absolutely true every time. How do we do CPT? Well, very easy. We multiply before and after by I, K, and minus J and J. How do we do bosons? Well, we do them like that. And we see that we can't have a massless spin 0 boson because it would 0. I'll continue here. 4 creation and what does the fermion structure mean? It's got 4 creation and 4 annihilations. How do we do 3 bosonic states into a baryon? Well, we do it that way. We can also show that the vacuum energy, the self energy term automatically cancels itself in this formalism. There's no problem with renormalization at all of the self energy term. It cancels to 0. It reduces to arithmetic to do it. Okay, and that's how we do a 3-component object like the baryon. And what we see is that it has the SU3 structure and that it solves the mass gap problem and many others. We can also apply it to the standard model. We can apply the same algebra to the standard model. However, I can't go into that now. Okay, thank you very much.
Okay, thank you very much to you for your presentation. We are here in the chat for question and answer. One question, can you see that?
It says, please send a copy of the slideshow to Luco. Is that what it is?
That's not a question.
That's, yeah.
No, okay, I can read the question.
Can you read the question to me? I don't know what the question is.
Dear Peter Rowland, do you think the Dirac equation describes an electron, a positron, both, or many particles?
Yeah, it depends which term is on top. If it's on top, it's an electron. If it's the second term that's on top, it's a positron. It describes either depending on what you put into it, whether you put the pluses and minuses. Lou's got a question.
Yeah, looking at things your way, you see the standard model through this lens.
Yeah.
What do you see beyond the standard model looking through your lens?
Well, I can't answer that immediately, but I have seen quite a bit beyond the standard model, because I mean, mostly it comes up with the standard model, but it doesn't rule out other things beyond it at all in any way. And I can see things like thermodynamics come out of it and things like that. And I can see how more unusual kinds of structures can come out of it. But I couldn't do them without mathematics. I can't just explain them verbally. Yeah, well, that's the Cooper pairs and stuff what I've mentioned.
Excuse me, go ahead. I thought that you can hear in the conference.
Yeah. Okay, can I just take a note of this? Okay. Is that the final question for the moment?
No more questions.
Okay, so I'll come out of this, stop video. Stop share.
Thank you very much. The next speaker will be our previously scheduled
I wanted to ask a question.
Fernando.
Is there any question I can ask to Professor Rowland, please?
Yes.
Professor Santilli, yeah.
Yes, Professor Rowland, how are you? We know each other since quite some time.
Yes, we do, yeah.
Yeah, we missed you at our 2020 International Teleconference because your very nice monographs on the Dirac equation came about. There was quite some discussion, but I have to tell you that you are the expert in that particular field, so we were unable to answer the question. If you want, I'll be happy to tell you the question very quickly. The question was, the theme of the conference was, as you know, that the historical Einstein-Podolsky-Rosen argument that quantum mechanics is incomplete. Yes. So the question was raised among the variety of lack of completeness. There was the issue as to whether charge conjugation is indeed complete, because certainly is conjugate the charge. However, does it conjugate also from matter to antimatter? And a number of opinions were expressed that no, that is not possible with the charge conjugation. The reason being because charge conjugation is an endomorphism in the Hilbert space. So both particle and antiparticle have a positive energy, having positive energy, they cannot annihilate into light. So the question, as you know, from all the discussion, we try to bypass this problem by completing charge conjugation into isoduality, which is essentially an anti-Hermitian map of everything, not only of the wave function, but also space-time, etc. In this case, the antiparticle have negative issue, have negative energy, so therefore, at least we start to initiate the representation of annihilation. The question that was raised was the following: whether by using your axiomatic structure, is there any possibility, here is a point, of achieving a quantitative numerical representation with the equation of the particle-antiparticle annihilation. The question was connected to when you wrote, remember when you wrote your beautiful monographs, I made a suggestion to you very, very humbly to see whether you could incorporate an additional axiom of the Dirac equation, which is iso self-duality, namely...
Well, I have done an iso version of the Dirac equation. I've done it at a meeting that you were organized. I did an isodual version of the Dirac equation. You may remember that.
No, this is a property of the isodial, because the one component, there are many interpretations. Your interpretation is not in question. Let me clarify, because there are many interpretations of the Dirac equation. That's the beauty and the beauty of the equation. One of the beauty of the equation. No, in our interpretation, half of the equation represents the electron, so the energy is positive. Yeah. And as you know, the fourth diagonal, the fourth gamma is positive, but you go to the other half, the fourth gamma is negative, and therefore this gives you a hint that it is indeed iso-self-dual. So therefore, I am convinced the axiom is mathematically unquestionable. What is questionable, debatable, is the physical interpretation, of course.
Okay.
But my personal opinion is that if you extend your but this is maybe I apologize with you in advance, but I'd love to discuss it with you, whether your axiom, because they are beautiful. Remember, I expressed my view to you in the past about the beauty of your axioms, and so whether they can be formulated, completed, I should say. Now the word completed is used everywhere. So I almost every week I receive lack of communication or lack of completeness of quantum mechanics. Is the real edge at this moment.
Okay, but I'm saying I have done the mathematical side of it. I've done an isodual version of the equation in this format.
I'm sorry, can you repeat?
I did write down an isodual version of this equation in this format.
But that's not
just a matter of how you interpret it.
No, it's not my point. No, what you did is fine, no objection. No. My point is a different one. I'm talking about the invariance of the Dirac equation on the iso-self-duality,
yes,
which is a map of the equation under itself. But it's dual, however, is represented with an hyperstructure. One part of an hyperstructure, there's one space-time for particle, is a separate space-time for antiparticle. They are combined as an hyperstructure. The unit has two dimensions. So all products have two values, and et cetera, et cetera, et cetera. So the question is that invariance. Once you have that invariance, then a quantitative representation of annihilation appears. I beg you, what I'm saying that this is terra incognita, so it's just discussing.
Okay, I think we should discuss this separately, though, because we're holding up the next speaker.
Yes, of course. Now, just wanted to bring to your attention.
Thank you.
Because,
yeah. Okay, thank you. Yes.
So we missed you. We miss you, Professor Roland. We miss you.
I don't remember being invited, but you probably invited me at a time when I couldn't come.
You were invited to be a member of the organization committee. Maybe you didn't receive. Professor Dunning-Davis from University of Hull.
I don't remember getting that.
We asked Professor Dunning-Davis to contact you. Sorry, we got to stop this.
Could you discuss this discussion? Continue this discussion offline.
I'm sorry, I apologize. We are friends. We know each other since a long time.
Yes, of course. I just want to invite our previous speaker who had technical difficulty, and please don't stress. I hope that everybody agree that because after your talk, we have this long 1.5 hour lunch break, so we can use some of this break. So you will have the full half hour for your talk, despite that we are starting late. So please, we are inviting this for the second time,
Fernando Velázquez Quesada.
Multigraphs, modeling hierarchical structures and scale change. Please, and everybody. I hope that now we'll have connection.
Me too. My apologies to everybody for the issue, and I will try to make this a little bit shorter so we don't lose a lot of time for lunch, which is of course important. As I was saying, let me start again. The presentation is about multigraphs of multigraphs, and it is about some discussions that I had the opportunity of having with Professor Osiewicz when I was a master's student around 15 years ago. And again, as I was mentioning before, As you know, Professor Osiewicz was very interested and enthusiastic about category theory. And in fact, he thought that category theory should be the basic language of mathematics, taking the place that set theory has nowadays. But again, even more, he was not only interested in making category theory the basic, the foundations, the basic language of mathematics. He was interested in being sure that everybody was going to have the chance to learn what category theory was about. And that means that he wanted to develop some form of lecture notes in which, in a stepwise fashion, in a most pedagogically possible way, we could introduce the notions of category theory for students at essentially any level. Of course, PhD students, master students, bachelor students, even high school students, and even below that. And the idea that Professor Osiewicz had was to start with a very basic notion, which is a graph, a single graph, and do a couple of things. First of them, realize that even though a graph represents morphisms between abstract objects, we can also have morphisms over these morphisms themselves. And in that way, we can construct more and more complex morphisms, as many as we want. And that's one aspect. The second aspect is he also wanted to be able to take a look at the graph and look not at adding more morphisms, more complex morphisms, but rather looking at these abstract objects that we have. And if we find out that they have a more concrete, or rather a concrete and a more complex structure, then use that for the structure that we are working on. And then, of course, making more complex these abstract objects, that means that the morphisms between them, they are going to become also more complex, or at least they're going to have a concrete definition instead of being just abstract morphisms. So I'm going to be, I will try to be a little bit faster, but hopefully still clear enough. Many of these notions, I'm pretty sure they are already existing in the literature, and the only difference could be the way of introducing them in a kind of uniform way, hopefully. So the very basic idea is to start with the notion of a graph, which in this case is a notion of a graph that is actually defining a directed graph in which the edges have directions, and one in which we allow multiple edges between a given pair of objects. It's important here that the objects, the elements of this set, this collection G0, are going to be called zero cells, and the edges between those objects, between the zero cells, are going to be called one cells. You can see, you can identify them by means of the colors in the diagrams that we will see. The two maps, they refer to the fact that we want to know, given each one cell, we want to know, or we need to know, which one is the source of that one cell and the target of that one cell. We can put those two maps together by defining a map that is called type, which returns essentially the same pair, the source and the target of the given one cell. So what I was mentioning, I don't remember if I actually had the chance to mention it, is that a graph, it's good enough for a lot of different applications, but it might not be enough for some of them. And in this case here, the example was to show that there are highways between two cities, for example, two highways between Mexico and Puebla, but then there might be also ways of moving between from one highway to the other. Particularly, you might have small towns while traveling one of those highways, and by crossing them, you might reach the other highway. So if we want to represent something like this, then we need something more than what a simple graph provides. And the idea was to take something that is called a two graph. It is now a structure that has three collections. It has the zero cells of before, the objects. It has the one cells, which are the morphisms between the objects, the zero cells, and the two cells represented in pink in the slides, which are morphisms over the one cells. The maps, they are indicating, given a one cell, which one is its source and its target, and likewise, given a two cell, indicating which one is its source and its target. And these two cells, they can only relate one cells that have exactly the same type, as it is shown in the diagram below. We have three one cells, F, G, and H, and we have one two cell alpha. And as you can see, alpha, which is relating which is mapping, which is taking us from F to G, it's properly defined because F and G have exactly the same type, from A to B. And then, of course, if we build this, or if we buy into this idea of there are objects, the zero cells, morphisms between those objects, the one cells, and morphisms over those morphisms over objects, the two cells, then we can just create as many I cells as we want. And that leads to the concept of an N-graph, which is formally defined as n+1 collections and 2 N maps. Essentially, each one of the collections contains 0 cells, 1 cells, 2 cells, up the way up to N cells. In the two maps, they are telling us for each I cell, but well, for each I cell minus the 0 cells, the basic ones, telling us which one is the source and the target of that I cell. And those I cells, the ones that have source and target, they should satisfy the following property. The source and the target, they should have exactly the same type. So some quick examples in diagrams, a tree graph, which as you can see now we have purple arrows, the three cells relating two cells, in this case sigma over here and a little bit below rho. An N-graph can also deal with representing a standard graph, which in this context with this terminology is nothing but a one graph. We can also have collections, that is zero graphs, in which we only have the collection of 0 cells, G0, and that's it. Now, I'm going to skip this. This was just about a name. And the important thing is that so far this construction is only about adding more and more complex morphisms that are acting over the ones that were previously the most complex morphisms. But we can do also something slightly different. Instead of thinking 0 cells, 1 cells, adding 2 cells, adding 3 cells, and so on, we might want to start with this graph. And instead of looking at higher levels of morphisms, just look at what each one of the 0 cells, the objects of the one graph are. And if in this case, or if it happens like it's being described here in the diagram, if we find out that the one graph, the 0 cells in this one graph happen to be 0 graphs on their own, then what we have is a structure that is called a 1-0 graph, which is depicted in the diagram that you can see here. We have 0 cells A, B, and C. We have 1 cells F, E, H, I, and each one of the 0 cells is in turn a 0 graph. Now, the most important thing here is that by giving a concrete structure to each one of the 0 cells A, B, and C here, they are now 0 graphs. That means that we also need, or we get a concrete definition for the 1 cells F, G, H, and I that are relating them. They are not just abstract morphisms anymore. In this case of a 1-0 graph, the 1 cells which are now morphisms between 0 graphs are called 0 prefunctors. Formally, a 0 prefunctor F from a 0 graph G to a 0 graph H is given by a map that is taking 0 cells in G and returning 0 cells in H. And then, of course, when we were doing this, taking a closer look thing, we might have found out that the 0 cells in the one graph that we had happen to be also 1 graphs on their own. If this is happening, then what we have is a structure that is called a 1-1 graph, which is again a 1 graph, the first one that we have here describing the external structure, and the other one is describing the internal structure of each one of the 0 cells of the graph, of the one graph. So we get something as it is shown in the diagram here. And once again, the fact that the 0 cells become more complex, it means, well, concrete and more complex, it means that the 1 cells relating them, they become concrete and more complex. So before we saw that a morphism between 0 graph was called a 0 prefunctor. Now a morphism between 1 graphs is going to be called 1 prefunctor. And it's formally defined as 2 maps, the first one taking 0 cells in G and returning 0 cells in H, and the second one taking 1 cells in G and returning 1 cells in H, just as it is shown in the diagram below here. For all of you familiar, which I guess is most of you, with category theory, then you know that there are several ways. There is at least two ways of satisfying this diagram here. And this gives rise to two different types of free functor. I'm going to skip these definitions. It's just pointing out that you get different types depending on how they behave, how they deal with the arrows in the source graph. Covariant prefunctors, they preserve the direction of the arrows. Contravariant prefunctors, they inverse, they take the arrow in the opposite direction. But the important part here has been that every time that we make a more precise description of the zero cells in a graph, we need or we get a more precise description of the one cells relating those zero cells. And in general, if by making this zooming in, we realize that each one of the zero cells is an N graph, then what we have is a structure called one N graph. And once again, now that the zero cells are N graphs, the one cells become something more complex, more concrete and more complex. They are now morphisms between N graphs, and they are called N prefunctors, which are formally defined as an N+1 collection of maps, each one of them taking an I cell in G and returning an I cell in H. The diagram that we have here, you might recognize several instances of the diagram that was defining a one prefunctor. We have one of those squares here, another one of those squares here, and so on. So if we had two different types of one prefunctor, because of the two different ways of satisfying this square, this part of the diagram, that means that now we have even more different types of N prefunctor, each one of them according to the way in which this diagram, this first square is satisfied, the way in which the second square is satisfied, and so on. So this part was then all about taking a one graph and taking a closer look at the zero cells and realizing that they might have a more complex structure. And of course, noticing that by making more complex or more concrete what the zero cell is, then we get a more concrete, a more complex and concrete definition of the one cells relating them. So now what happens if what we take is not a one graph, but a two graph to begin with? And what happens if by taking a closer look at the zero cells, we realize that each one of them is an N graph? Then what we have is a 2N graph, which is again a two graph in which each one of the zero cells is an N graph. So if making this zooming in, if giving a concrete structure to each one of the zero cells gave us a more concrete and complex definition for the one cells, now the same is going to happen for the two cells that are relating those one cells. Particularly, if we happen to take a 2-0 graph, then two cells in a 2-0 graphs are going to be called zero pre-transformations because they are morphisms between zero prefunctors, this F and E here, which again in turn happen to be morphisms between zero graphs A and zero graph B. At this point, a zero pre-transformation is just an abstract morphism, but things become interesting when we look at a two cell now in a 2-1 graph. Now, a two cell in such a structure is a morphism between one prefunctors, which remember are morphisms between one graphs. And formally, a one pre-transformation is given or is defined by, is given by a single map, a map that is taking zero cells in G, the source of both one prefunctors, and is returning a one cell in H, which is the target of the two one prefunctors. And the cell that we are obtaining in H, the one cell, is not just any cell. It's one that is connecting the image of the object under F with the image of the object under E. So in more practical pictures, a one pre-transformation does what this diagram shows. We have two graphs, two one graphs, G and H. We have two one prefunctors between them, F and E. We have a one pre-transformation alpha, and this one pre-transformation is taking this object A, this zero cell in G, to a one cell in H, which is connecting F of A with E of A. So that's what happens when we look at a two cell in a 2-1 graph. But then what happens when we look at a 2-cell in a 2-2 graph? Well, it's just a generalization of what happened before. Now a 2-cell in this structure is a morphism between 2 prefunctors, which are again in turn morphisms between 2 graphs. And is formally defined as now 2 maps, one of them taking 0 cells in G and returning 0 cells in 1 cells, sorry, in H, and the other one taking 1 cells in G and returning 2 cells in H, as described in this diagram that we have over here. And those 2 maps, alpha maps, they should satisfy requirements analogous to the previous ones. And this is a 2-pre transformation at work. You can see how besides mapping objects A and B into 1 cells in H, it is also mapping the 1 cell F into a 2 cell in H. Okay. And then in general, what is then a 2 cell in a 2n graph? Where is something that is called an n pre-transformation, and that is being formally defined as a collection of n maps, each one of them taking an I cell in G and returning an I plus 1 cell in H, as it is shown in the diagram. This diagram then we have in the above part the n graph G, below the n graph H, vertical going down the 2 n prefunctors F and E. In diagonal then we have our n pre-transformation alpha. And again, alpha should satisfy a requirement analogous to the previous cases. So that happens when we take a 2n graph. But if we start, instead of with an n graph, we start with an n1 graph, something more general, and we realize that the 0 cells happen to be n2 graphs, then we get a structure that is called n1, n2 graph. In this structure, then, the 0 cells are again n2 graphs, which means that the 1 cells are now n2 prefunctors, and they have a precise definition as before. The 2 cells are now n2 pre-transformations, and they have a precise definition as before. The same happens with the 3 cells. They have a precise definition. They are called n2 pre-modifications. And here is a description, a definition of what an n pre-modification is. Essentially, the idea is that if the n prefunctors are working vertically and the n pre-transformations are working 1 step in diagonal, then an n pre-modification works 2 steps in diagonal, taking I cells in G and returning I plus 2 cells in H. Here are some quick examples that I'm not going to discuss in detail, just saying that an n pre-modification becomes interesting once that we are working with 3-2 graphs, which is where we may draw 2 cells in the target graph. Here is something a little bit more complex. We have a 3-3 graph. Each one of the 3 cells is a 3 pre-modification, and it does 2 things: taking objects in G to 2 cells in H, and taking 1 cells in G to 3 cells in H. So this is what happens when we are thinking about these structures N1, N2 graphs. But then we can just keep going, keep generalizing, and reach the idea or the concept of an N1 all the way up to NK graph. This structure is defined in the following way. If K is 1, meaning that if here in this tuple we only have 1 number, then what we have is simply an N1 graph, and that's it. But if we have more than 1 number, then what we have, as in this case N1 all the way up to NK, what we have is an N1 graph, the first index indicating the external structure of the graph, and the rest of the numbers N2 to NK describing the internal structure of each one of the 0 cells. Terminology then is just a generalization of what I mentioned before. We take N1 NK graph, that means that the 0 cells are N2 to NK graphs. The 1 cells which are relating these kind of graphs, they are called N2 NK prefunctors. The 2 cells which are relating N2 AK prefunctors are called N2 NK pre-transformations, and so on for the concept of premodification and whichever other name we want to choose for 4 cells, 5 cells, and so on. So I'm going to then essentially what we have been doing, or what is the idea of this stepwise construction of concepts that will eventually relate to category theory. The idea is that if we start with an N2NK graph, then we might think, we might realize that we have this kind of graph, we might have many others of these kind of graphs, and there might be morphisms between them. Morphisms between these graphs, morphisms between them, morphisms between these graphs, and so on. So that means that we can go one level up and then create a structure called N1, N2, and all the way to NK graph. This is by taking a step back, looking at a collection of these objects and looking for the morphisms between them, the morphisms between the morphisms between them, and so on. On the other hand, what we can do is look at these kind of structures and then try to find out if the 0 cells, the guys here, they have a further more precise structure. And if they happen to be, for example, NK plus 1 graph, then what we actually have is an N1, N2, all the way to NK plus 1 graph. So just to round up the final things, three important points. Again, this is not about, or this presentation was not about interesting technical results or new research. It was essentially the idea of Professor Rusiewicz of trying to provide a more pedagogically way of introducing category theory to students of any academic level. Because again, one of the most important things for him was that category theory should be available for everybody. Everybody should be able to understand and to know what category theory is. And the second one, again, all of you know already, category theory, the most important point is the emphasis that it makes on the morphisms, on the relations, to use another word. And this is also something that I think applies to Professor Rusiewicz, at least in the academic life in which I happen to be lucky enough to meet him. He, or as good as a researcher as he was, and he was an amazingly good one, one of the most important things was the relations that he was creating with other researchers. And in that way, well, in particular with students like myself at the time, and the way that with that, he was inspiring and encouraging us to explore things, to do more research, to understand things in a better way. So if I have something to say to close this presentation is, indeed, as in category theory, the relation that we establish with our academic partners are the most important things. And I thank Professor Rusiewicz for teaching me not only about category theory, but also for teaching me this. Thank you very much.
Thank you, Fernando. Go ahead, Hannah. Excuse me.
We have two questions. I think that we have 3 questions to the speaker. The first one from Michelle Hader. What do you mean, Michael Hader? What do you mean by graph? Is it usually a set theoretic concept and categories are not?
The definition that we were providing, that was provided, was in particular was just a structure that has 2 collections and in which one of those collections is or represents objects in which we don't go into detail about what they are, and the second one are morphisms between those abstract objects. And as I was mentioning, formally or more precisely, what we are defining is a notion of a graph that is directed graph and that allows multiple edges between a given pair of nodes of objects. Whether it is a theoretical or category theoretical definition, we rely on the idea of collections. So indeed, it needs some idea of sets to begin with. But I think the interesting part is that little by little, with all these constructions, what we are doing is emphasizing the fact that morphisms are the important ones. That even though we start with these abstract objects, we add morphisms to them, we add morphisms over those morphisms and so on. And also not only in this upwards direction, only in a downwards direction, looking at those abstract objects and realizing that they might be also collections or in general just graphs, that means collections of objects with more morphisms between them at a different level. So I wouldn't be able to say exactly whether it is set theoretical or category or categorical. I think it's just kind of slowly and stepwise way of introducing or presenting eventually notions of category theory.
Oh, excuse me. We have one more speaker, and maybe we have not more time for the next question. But you can see those questions in the chat, question and answer that you have access, and then you can answer in this way, please.
Yes, I will do. Thank you very much to everybody.
Okay.
Thank you. Thank you. Thank you.
Okay. Now you are going to present Alberto Braque. Okay, excuse me. Then the next speaker is Alberto Fragio. He is going to present the speech Zbigniew Osiewicz, Karl Popper y el mito del marco. Alberto,
yes.
It's your turn, please.
Thank you very much for this opportunity to share some thoughts about Zbigniew philosophy of science and his criticism to Karl Popper. I have a PowerPoint presentation. Well, I will start with a summary of my talk. I have the slide in Spanish. Sorry for that. The point I want to argue is concerning one of Zbigniew's papers entitled "Science Must Never Be Objective." In this paper, Zbigniew argues that one of the most important problems in philosophy of science is to guarantee the freedom of thinking and the pacific coexistence among rival alternative theories. So in this way, Zbigniew defended a kind of a normative, pluralistic, normative epistemic pluralism, openly anti-Popperian, that was quite close to relativism and anti-realism. From his point of view, the Popper philosophy of science is a way to limit the free of thinking as far as the falsification methodology is in fact a dispositive to stop and to extinguish new ideas. Well, so far as the promotion of free thinking and scientific pluralism has the effect to promote disagreements, in this talk, I will argue that the positive consideration of scientific disagreement makes a sort of connection between Zbigniew and Karl Popper. Well, from Zbigniew's philosophy of science, my point is we might conclude also a refuse of what Popper called the myth of the framework, el mito del marco in Spanish. That is to say, the belief about the impossibility for a researcher to solely come out from the framework of concept and principles within in this framework, which he's working, and to make a comparison between another frameworks in another rival frameworks. Then I will argue that if Zbigniew was, we may say, skeptical about the successful resolution of scientific disagreement, his defense of open plural science would involve a refusal of the myth of the framework, and in this point he would agree with Popper. Well, concerning the objection of Zbigniew to Karl Popper, it was concerned mainly about these two famous books, Karl Popper books. One of them is Objective Knowledge, and the other one is the very famous book, Popper books, The Logic of Scientific Discovery. In this paper, Science Must Never Be Objective, Zbigniew criticized to Popper the assumption that the aim of the science is to provide a unique, correct explanation, and that the criterion, the Popperian criterion between science and pseudoscience is based in this assumption. Well, here, I don't know if you can see that. He says, sorry. Well, I may read, because I don't know if you can see that. He says, the proposal about the demarcation is based on two assumptions. The first one is that the unique aim of science is to explain nature. And B, the second one, that there is one nature, therefore must be only one explanation, only one unique, correct theory. So, from Zbigniew's point of view, Popper understands the science mainly as empirical science. An the deduction and the a priori conceptual structures have an important, a key role regarding the process of validation, Popper says refutation, of the scientific statements. In particular, the scientific ideas allows, according to Popper, to conceive or to think about a priori possible experiments in the way that each scientific idea must have a crucis, a experimentum crucis, no, a crucial experiment for test about the empirical content of the idea. In this way, the pseudoscience will be that has not experimentum crucis. That is to say, that it's not possible to conceive a priori crucial experiment. So, in this sense, Zbigniew make the following criticism. Popper considered that the theoretical speculation, we can also introduce mathematical speculation maybe, must be subordinated to the empirical content of science. In this way, the free of thinking without empirical content will be pseudoscience. No? In particular, he says garbage science, no? Ciencia basura. For this reason, Popper's philosophy of science will limit the free of thinking so far as the falsification or falsation methodology is in fact a dispositive, a mechanism for stop new ideas in the way that they extinguish imagination in the process of waiting for experimental results. This is the first Zbigniew criticism to Popper. The second one is inspired in the historical works of Imre Lakatos. We have here two of them. And Lakatos, the history of science produced by Lakatos, shows, according to Zbigniew, that the experimentum crucis are not always possible. Moreover, the experiments usually are object of many controversial interpretations. The third criticism is that if we admit that the refutation by empirical experiment is more scientific than experimental confirmation, the difference between confirmation and refutation, according to Zbigniew, is not the main point. Because the main point is the question of the freedom of thinking in science. Well, I will go very quickly to the main ideas of Zbigniew's philosophy of science. The first one is that science, understood as a set of ideas or rival statements, the science must not be evaluated according to a criteria that produce a unique winner position against a big quantity of loser position. Quite the contrary, the science has a plural nature, and it's good that the science is in this way. Well, the second main idea of Zbigniew's philosophy of science is that the coexistence of alternative subjective visions must not be considered as a provisional or transitorial stage of the science, but quite the contrary, this coexistence of multiple perspectives is the normal stage of science. Well, with these statements, Zbigniew proposed that the historical development of science must not be considered as a sort of convergence towards a unique, correct vision of the world, nor a sort of construction of a universal agreement. Indeed, he says that several historical episodes shows that scientific community may be wrong, but maybe a very short minority have reason. Well, this fourth point is quite controversial, and it comes from another Zbigniew paper. The title is "Are Peer Review Guardians of the Truth?" and says that the scholar, the dominant scholar understanding might block the existence of rival theories. And he considered that this sort of unique vision of reality, of science, is defended by the peer reviewers. Well, this is an important point in the Zbigniew philosophy of science. He said that the peer reviews must not be considered as the guardian of the truth, but quite the contrary, the peer reviews, the anonymous peer reviews, are only guardians about his personal vision. Well, he used a metaphor to explain this idea. Is the metaphor of the crucible in Spanish is un crisol, that is a cavity in ovens that receive the molten metals. Well, he says the subjective personal views of anonymous reviews must not be considered to be a crucible in which ideas are tested. Similarly, they must not be considered a venue in which broad ideas are disproved and disproved disagreement is refuted. Well, according to this point, the 6 is even more controversial. He says that the presence of anonymous peer reviews makes a damage in science because it makes problematic the open scientific discussion. The scientific evaluation must be public, not anonymous. Well, he has this question, is why is that referee who supposedly so great in prose a submitted paper must remain anonymous and cannot be named? Well, the diversity of opinions, according to Zbigniew, is fundamental for any science. And since the consensus is a damage for science, the disagreement is the effective way that the science progress. Well, he says literally, different opinions are not only good thing, they are necessary for science. Well, that is why he concludes that science must not be objective. Indeed, he says objective science is dead science. Well, he also added the scientific, the scholar world embrace only one vision of science as necessarily objective, and such does not allow for alternative theories. This parochial attachment to a singular and monolithic vision of objective science is harmful. Well, the last point I want to present, according to Zbigniew philosophy of science, says that there is not a criterion that allows to establish a demarcation between science and pseudoscience. He says there is one and only one science, and that is a collection of subjective, personal, individual, alternative ideas. Well, the second part of my talk tries to make a relation between Zbigniew, Thomas Kuhn, and Karl Popper. Zbigniew, as I try to show, defended a sort of normative epistemic pluralism, openly anti-Popperian, that if this perspective would promote the free of thinking, it also was very close to relativism and anti-realism. Well, two philosophers of science, Kinzel and Kuss, has made reference to a tradition in philosophy of science that relate relativism and disagreement. In particular, Martin Kuss remembers that epistemic relativism must not be considered as a unique position, but as a spectrum of position. Well, I propose to explore this argument in few minutes concerning the famous debate, the famous disagreement between Popper and Kuhn in the occasion of a symposium held in London in 1965, organized by Imre Lakatos and Alan Musgrave. This very famous symposium was aimed to discuss the book, the Thomas Kuhn book, The Structure of Scientific Revolution. Well, I have still a few minutes, 5 minutes. Well, Popper considered the early Kuhn, the early notion of Kuhn of the paradigm and the incommensurability as an instance of what he termed the myth of the framework. That is to say, the belief about the impossibility for a researcher to come out of the framework of concepts and principles and to compare it with another framework in competence. So with this myth, Popper defended the contrary thesis to Kuhnian incommensurability. In his opinion, always is possible a critical discussion and also the comparison about rival intellectual frameworks. Well, from the point of view of Karl Popper, the communicative breakdowns in science must not be considered regarding not shared and incommensurable assumption, but because of the will to overcome these communicative breakdowns and the lack of a true critical spirit or attitude. Well, Popper considered himself a sort of critical rationalist, and he saw in Kuhn works an example, a model about irrationalism and relativism. Well, I will jump this because of time. Kuhn answer to Popper says that if it's so easy to overcome, to come out from our framework and to compare it with another rival competitive framework, then it must be completely easy to evaluate foreign framework. But happens quite the contrary, that the frameworks grid on the mind, and is not so easy to broke that frameworks and to be overcome the frameworks. Kuhn says in order to be able to broke the framework before the framework must be live and explored. Well, he also say if a framework, a conceptual, we also may add a mathematical framework, must not be at the same time essential for the research and something that we can't throw out. Quite the contrary, it would happen with, as in the famous Groucho Marx joke, no? Those are my principles, and if you don't like them, well, I have others. Well, I will jump this. I go to the conclusion. The conclusion that I want to argue is that Zbigniew agrees. I believe he agrees with Popper when he considered that the diversity and the disagreement makes progress the science, and that the consensus provokes the decadence in science. But the Zbigniew defense about the free of thinking and the multiplication of scientific disagreement will involve a refusal of the myth of the framework, as far as the discussion between rival position are indeed a desirable state in science, because it allows scientific progress. However, and in this point, as Zbigniew will be more close to Thomas Kuhn, was quite aware about the difficulties in the moment to persuade to the elders about the validity of their own position. And indeed, he was quite skeptical about the successful of the discussions. He says, I quote, an attempt to share an idea, for instance, with a referee who protects the dogmatic consensus could be dangerous. That is why Zbigniew recommends that instead of try to pursue the other people, one must start to pursue to oneself. Well, thank you very much for your attention.
And thank you, Alberto, for your presentation. We have not questions in the chat, and maybe for the time, we can stop here now because we have to start at 14 o'clock. Then we have one break of 25 minutes only. Are you going to say something, Hannah? Excuse me.
If I, I apologize. If I have 1 minute, I would like to express my deep appreciation for the speaker. His talk has been magnificent, and I believe his talk is very important for contemporary physics. I wish him, I'm sure he will publish a paper. I am at his disposal to help him to disseminate his paper all over the world. I only have a very quick, very short comment due to short of time to indicate that in my numerous exchanges with Professor Odziewicz, he was additionally to everything that the speaker has so nicely presented. In addition to that, Professor Odziewicz was very supportive of the last monograph by Sir Karl Popper, with the title, a very evocative title of The Schism in Physics. In particularly because Karl Popper and as well as Professor Odziewicz, they were both very supportive of the EPR argument that quantum mechanics is not complete. And I remember Professor Odziewicz was very happy when I used to tell him by phone or the quotation in Sir Popper, both get the quantum mechanics should be called an atomic mechanics because it provides only exact value only in atomic physics. But you go to nuclear physics, you have never represented nuclear magnetic moment. Spin, we don't understand the spin one of the deuteron. The list is monstrous of insufficiency. In chemistry, those are all things that were discussed with Professor Odziewicz. In chemistry, quantum chemistry has been unable to represent the attraction between the valence electron because the high school student can calculate the Coulomb repulsion among identical electrons against the physical reality, which is they attract each other. The Coulomb repulsion 230 Newton, etc., etc. So that's why we are in the science in a very deep crisis, particularly for the issue raised by this speech. That I conclude by saying, expressing again my congratulations and suggestion to propagate the thinking and the paper as widely as possible. Thank you. Thank you.
Thank you very much for this insight. Thank you very much, Professor.
Okay, then we are now to make the break. And recommend you to start in 20 minutes almost. There are going to be some presentation, I think, for the Cultural Center. I don't know if Vanessa ¿vas a presentar algo?
Sí, sí va a presentar ahorita, perdón. Okay. Sí va a presentar, está Patricia Torres conectada y ella va a mandar la señal para la presentación de la actividad cultural.
Ok, adelante para poder reiniciar a las 4.
Sí.
Buenos días a todos y bienvenidos al concierto de la Orquesta Filarmónica de la UNAM. Como ha escuchado ya, yo soy Massimo Quarta, soy italiano, soy violinista y conductor. Y soy el nuevo director artístico de la UNAM. Primero me disculpo para mi español,